Langchain Voyage AI Embeddings. NaN. A tool for generating embeddings using the Voyage AI application programming interface. Embeddings are numerical representations of text that capture the semantic meaning of the text. They can be used for various natural language processing tasks, such as text similarity search, clustering, and classification. Inputs. The text to be embedded. This could be a sentence, a paragraph, or a whole document. For example, the quick brown fox jumps over the lazy dog. The name of the Voyage AI model to be used for embedding generation. Voyage AI offers various models with different levels of accuracy and performance, each designed for specific tasks. For example, text embedding ADA002. Outputs. A list of numbers representing the embedding of the input text. Each number in the list corresponds to a specific dimension in the embedding space, which is a multi-dimensional space where similar texts are located closer to each other. Steps. The tool first receives the input text. Then, it sends the text to the Voyage AI application programming interface along with the specified model name. Finally, it receives the embeddings from the Voyage AI application programming interface and outputs them. Prerequisites. A Voyage AI application programming interface key is required to access the Voyage AI application programming interface. You can obtain a key by signing up for a Voyage AI account. This key is used for authentication and authorization. For example, SK or a P key. The name of the Voyage AI model that you want to use for embedding generation. For example, text embedding ADA002. Fine-tune parameters. The specific Voyage AI model used for embedding generation. For example, text embedding ADA002. The number of dimensions in the embedding space. A higher dimension generally leads to a more detailed embedding but can increase computational cost. For example, 1536. Challenges and fixes. The Voyage AI application programming interface has rate limits in place to prevent abuse. If you exceed the rate limit, you will be temporarily blocked. For example, you have exceeded your rate limit. Please try again later. Contact Voyage AI support for assistance in resolving this issue. An invalid or incorrect Voyage AI application programming interface key will result in an error. For example, invalid API key. Verify the accuracy of your API key. If you provide an invalid model name, the tool will be unable to find the model and will generate an error. For example, model not found. Ensure the model name is valid. Network connection issues or problems with the Voyage AI application programming interface endpoint can cause errors during API requests. For example, connection refused. Ensure you have a stable internet connection. Check if the Voyage AI application programming interface endpoint is available. Retry the request after some time. Upstage Vector Store for Langchain Community. A summary of its features and usage. A vector store based on Upstage Redis. A fully managed in-memory data store with persistent storage. Upstage Redis offers high performance, scalability, and reliability, making it an ideal choice for vector search applications. Inputs. Embeddings. Numerical representations of text data. Embeddings are generated by embedding models, such as OpenAI's text embedding ADA002, which map text to high-dimensional vectors. These vectors capture the semantic meaning of the text and allow for efficient similarity searches. Text data. The textual content to be stored in the vector store. This can be anything from documents, articles, code, or even chat messages. Outputs. Vector representations of the data. The generated embeddings of the text data, stored in the vector store for efficient retrieval. Similar documents based on the query. When a query is submitted, the vector store finds the documents with the most similar embeddings to the query's embedding. This enables relevant document retrieval based on semantic similarity, rather than exact keyword matching. Steps: create an Upstage Redis instance. Provision an Upstage Redis instance, which provides the underlying storage for the vector store. Configure Upstage Vector Store. Initialize the Upstage Vector Store object with the necessary configuration parameters, such as the Upstage Redis connection details and embedding function. Add or update text data with embeddings. Store the text data in the vector store, along with their corresponding embeddings. You can either add new data or update existing data with new embeddings. Search for similar documents. Submit a query to the vector store. The store will then use the query's embedding to find the most similar documents from the stored data based on their embeddings. Prerequisites: Upstage Redis account. A user account with Upstage Redis to access and manage the Redis instances. Create a free account. Register for a free Upstage account at https://ups-com to get started with Upstage Redis. Upstage Redis connection details. The necessary credentials to connect to your Upstage Redis instance. Obtain from Upstage Redis dashboard. Access your Upstage Redis dashboard to find your Redis connection details, including the URL, token, and namespace. Fine-tune parameters. Embedding function. The embedding model used to generate vector representations of the text data. This is typically an embedding API, such as OpenAI's text embedding ADA 002 or a local embedding model. Redis URL. The URL of your Upstage Redis instance. This is used to establish a connection to the Redis server. Redis token and authentication token used to access your Upstage Redis instance. Redis namespace. A unique identifier to distinguish your vector store data from other data in the Redis instance. Challenges and fixes. Incorrect Redis connection details. Verify that the provided Redis connection details are correct. Ensure you are using the correct URL, token, and namespace. Check for typos or inconsistencies in the connection details. Verify connection details. Verify the connection details in your Upstage Redis dashboard and ensure they match the ones used in your code. Embedding errors. Check the embedding function and input data. Ensure that the embedding function is correctly configured and the input data is compatible with the function. Check embedding function and input data. Review the embedding function's documentation, input requirements, and any error messages generated during the embedding process. Search performance issues. Optimize the Redis instance for better performance. Consider scaling the instance to handle larger datasets or optimizing the search queries for efficiency. Optimize Redis instance. Use Upstage's configuration options to adjust Redis settings, such as increasing memory capacity or optimizing indexing strategies. Redis connection timeout. Increase the connection timeout limit to allow for more time to establish a connection. Increase timeout limit. Adjust the connection timeout settings in your code or configuration files to provide sufficient time for the connection to be established. Summary of Langchain Community Vector Stores. Upstage Vector Store. None. A vector store that utilizes Upstage Redis as its backend for storing and retrieving embeddings. Upstage Redis is a fully managed, scalable, and secure in-memory data store. It offers high performance and low latency for storing and retrieving embedding data. By leveraging Upstage Redis, Upstage Vector Store facilitates efficient and fast similarity searches in vector datasets. Inputs: text data that will be embedded and stored in the vector store. For example, You might have a dataset of product descriptions or blog posts. Each piece of text would be an input. Embeddings generated from the text data. Embeddings are numerical representations of the text data. They capture the semantic meaning of the text and allow for efficient comparison of text similarity. Embeddings can be generated using various embedding models such as sentence transformers, OpenAI embeddings, or other pre-trained language models. Outputs: retrieved embeddings that are most similar to a given query embedding. This is the output of a similarity search. A query embedding is generated from a search query, and the vector store returns the embeddings that are most similar to it. Text data that is associated with the retrieved embeddings. This output allows you to retrieve the original text corresponding to the embeddings found during the similarity search. Steps: initialize the Upstage vector store by providing the necessary connection details for your Upstage Redis instance, such as the URL and application programming interface API key. Add the text data and its corresponding embeddings to the vector store. This process involves storing the embeddings in the Upstage Redis database. Perform similarity searches based on the query embeddings. You provide a query embedding to the vector store, and it returns the most similar embeddings from the stored dataset. The similarity search is based on a chosen metric, such as cosine similarity or dot product. Retrieve the text data associated with the retrieved embeddings. After a similarity search, you can access the original text data that corresponds to the retrieved embeddings. Prerequisites: an Upstage Redis account is required to use the Upstage vector store. You will need to create an account on the Upstage platform. The Upstage Redis URL and API key are crucial for connecting to your Upstage Redis instance and using it as the backend for the vector store. These credentials are provided in your Upstage Redis account settings. An embeddings model is necessary for generating the embeddings that are stored in the vector store. Popular choices include sentence transformers, OpenAI embeddings, or other pre-trained language models. These models are capable of converting text into numerical representations, which are then used for similarity comparisons. Fine-tune parameters. The similarity metric determines how the similarity between query embeddings and stored embeddings is measured. Common choices include cosine similarity and dot product. These metrics define how the closeness between vectors is calculated, influencing the results of similarity searches. The number of results to return for similarity queries specifies how many similar embeddings are retrieved in response to a query. This parameter allows you to control the number of results you want to see for each search. Challenges and fixes. Connection issues with Upstage Redis may arise if the connection details URL and API key are incorrect, or if the Upstage Redis instance is not available. To resolve this, verify the accuracy of the connection details and ensure the Upstage Redis instance is running. Slow query performance can occur if the embedding model used is inefficient or if the data is not indexed properly for fast searching. Optimizing the embedding model and indexing data effectively can improve query speed. Limited storage capacity can be a constraint when dealing with large datasets. Upgrading the Upstage Redis plan to a higher tier with more storage capacity can address this issue. Alternatively, you can consider using a different vector store designed for larger datasets if necessary. Langchain Voyage AI embeddings. Langchain Voyage AI embeddings is a powerful integration that allows users to employ Voyage AI's vector database capabilities within the Langchain framework. This integration streamlines information retrieval and analysis by leveraging the capabilities of vector databases. Inputs: Textual data that can be processed into embeddings. These can be texts, documents, or articles. For example, a user might input a collection of news articles, scientific papers, or product descriptions for analysis. Outputs: numerical representations of input texts. These representations are called embeddings. Embeddings provide a numerical representation of the input texts, enabling efficient comparison and similarity analysis. For example, an embedding for a news article about artificial intelligence would be numerically similar to another news article on the same topic, but different from an article on a completely unrelated topic. Steps: processing and transformation of input text into a vector representation. The input text is first processed and converted into a numerical representation. This process involves understanding the meaning and context of the text, and then representing it as a vector. Generation of embeddings using Voyage AI embeddings. Voyage AI's embeddings are utilized to generate these vectors. Voyage AI offers a range of pre-trained models specifically designed for generating high-quality embeddings, capturing nuanced semantic relationships between words and phrases. Prerequisites: Voyage AI account is necessary for accessing the Voyage AI embeddings API. This account grants users access to Voyage AI's embedding service, including various pre-trained models and their associated API keys. Your Voyage AI application programming interface key is required for authenticating and accessing the service. Your API key is a unique identifier that allows you to access Voyage AI's services, enabling you to send requests and retrieve responses from the Voyage AI API. Installation of the Langchain library is required for integrating with Voyage AI embeddings. Langchain is a Python framework that simplifies the use of large language models and other AI tools. Installing Langchain allows you to leverage its functionality and seamlessly integrate with Voyage AI's embeddings. Execute the following command to install the Langchain library using the pip package manager. This command will download and install the Langchain library on your system, enabling you to use it in your Python projects. Fine-tune parameters. Voyage AI model selection. Voyage AI provides a selection of pre-trained models designed for specific use cases and tasks. Each model has its strengths and weaknesses. For instance, a model trained on scientific text might be better suited for analyzing scientific documents, while a model trained on conversational data could be more suitable for processing natural language. Embedding dimension. The dimension of an embedding refers to the number of values in the embedding vector. This value can affect the performance and efficiency of your application. A higher dimension often leads to more accurate representations but may require more processing power. Challenges and fixes. API key management. Keeping track of and securely managing API keys is crucial to prevent unauthorized access to your Voyage AI account. Consult the Voyage AI documentation for comprehensive guidance on managing API keys. The Voyage AI documentation provides detailed instructions on managing API keys, including best practices for security and storage. Embedding dimension selection. Choosing the right embedding dimension can be a balancing act between accuracy and computational efficiency. Conduct experiments by testing different embedding dimensions based on the characteristics of your dataset to find the optimal balance. This involves exploring the relationship between embedding dimension and the performance of your application, ultimately finding a dimension that delivers accurate results while minimizing computational cost. USearch is a vector store for Langchain Community. USearch is a vector store that leverages the USearch library for efficient similarity search. USearch enables you to store and retrieve textual data based on semantic similarity, making it ideal for applications like question answering, document search, and recommendation systems. Inputs: text data to be indexed. This includes the actual text content that you want to store in the vector store. For example, it could be a collection of articles, blog posts, or customer reviews. Metadata associated with the text data. Metadata provides additional information about the text data, such as the title, author, date of creation, or any other relevant attributes. This metadata can be used to filter or refine search results. The outputs: a list of relevant documents based on a given query. When you submit a query to USearch, it returns a list of documents that are most similar to your query based on semantic meaning. The similarity scores between the query and the retrieved documents. USearch provides similarity scores for each retrieved document, indicating how closely related it is to the query. Higher scores indicate a stronger semantic similarity. Steps: embed the text data using a suitable embedding model. An embedding model converts text into numerical vectors that represent the semantic meaning of a text. This process allows USearch to compare documents based on their underlying meaning rather than just literal word matches. Store the embeddings and metadata in the USearch index. USearch stores the embeddings and associated metadata in an efficient index structure. This index allows for fast similarity search. Search the index based on a given query by embedding the query and finding the nearest neighbors. To search for documents, USearch first embeds the query using the same embedding model used for the text data. Then, it finds the nearest neighbors in the index based on the similarity between the query embedding and the embeddings of the indexed documents. Prerequisites: USearch library installed. USearch library provides the core functionality for building and using the vector store. You can install it using the pip package manager. Pip install USearch. Embedding model available. An embedding model is crucial for converting text into meaningful vectors. Popular choices include sentence transformers and OpenEye embeddings. Sentence transformers, OpenEye embeddings, fine-tune parameters, embedding model parameters. These parameters control the behavior of the embedding model. For example, you might adjust the model architecture, the size of the embedding vectors, or the training data used to fine-tune the model for specific tasks. USearch index configuration. USearch index parameters influence the performance and efficiency of the search operation. You can adjust settings such as the index type, the number of dimensions for embeddings, and the search algorithm used to optimize for different workloads. Challenges and fixes. Index creation and update performance issues. Building and updating a large USearch index can take time, especially when dealing with massive datasets. Optimize USearch index parameters and configuration. Tuning USearch index configuration, such as the choice of index type or the use of data partitioning, can significantly improve index creation and update performance. Search performance degradation with large datasets. Search performance may degrade as the size of the index grows. Explore techniques like indexing strategies and data partitioning. Techniques like using hierarchical indexing, partitioning the data into smaller chunks, or using specialized search algorithms can help mitigate search performance degradation in large data sets. Langchain Community Vector Stores VDMS. A vector database designed for storing and retrieving embeddings, facilitating efficient search and retrieval based on semantic similarity. Inputs: text data that will be converted into numerical representations called embeddings. Embeddings, which are numerical representations of text data used for similarity comparisons. Outputs. Retrieved embeddings, representing the most similar items based on the input embeddings. Text data associated with the retrieved embeddings, providing the original textual context of the retrieved information. Steps. Creating a VDMS object. Initializing the vector database and setting up the necessary configurations. Adding embeddings to the database. Storing the numerical representations of text data for future retrieval. Retrieving embeddings. Querying the database using input embeddings to find the most similar entries based on semantic similarity. Prerequisites. VDMS installed on your system, using the package manager pip to install the required library. A vector database service available, such as AWS, GCP, or Azure, providing storage and querying capabilities for embeddings. Fine-tune parameters. Dimension of embeddings. Specifying the number of dimensions used to represent text data as numerical vectors. Database configuration. Setting parameters such as the database type, connection details, and indexing strategies for optimal performance. Challenges and fixes. High latency for large datasets. Experiencing delays in retrieving embeddings due to the volume of data. Using a faster database with optimized indexing and querying capabilities. Database connection issues. Encountering errors when connecting to the vector database. Checking database credentials to ensure they are correct and have the necessary permissions. Troubleshooting network issues. Verifying connectivity and addressing any network-related problems. Verifying database server status. Confirming the server is running and accessible. Restarting the server if it is experiencing issues. Retrying the connection to the database after addressing potential issues. Verifying the VDMS configuration. Checking the settings and parameters for accuracy and compatibility. Langchain Community Vector Stores WALD. A vector store implementation using WALD. An open-source approximate nearest neighbor and search library. To efficiently store and retrieve similar vectors. Inputs. Textual data that needs to be embedded and indexed for similarity search. For example, this could include product descriptions, articles, or customer reviews. Embeddings of the text data, which are numerical representations of the textual data. These embeddings are usually generated by an embedding model like sentence transformers, OpenAI embeddings, or others. Outputs. Similarity search results for query embeddings. When a query embedding is provided, the WALD vector store can return the most similar vectors and associated text data based on a specified distance metric. This allows for applications like finding similar products, recommending related articles, or understanding customer sentiment. Steps. Convert the text data into numerical vectors using an embedding model. This process transforms textual information into a format that can be easily compared and searched. Store the embeddings in a WALD index. WALD is a powerful library that efficiently stores and searches for similar vectors in high-dimensional spaces. Perform similarity search using the WALD index. When a query embedding is provided, WALD uses its approximate nearest neighbor search algorithms to find the most similar vectors from the indexed data. Prerequisites. WALD installation. The WALD library can be easily installed using the Python package manager pip. Pip install WALD. An embedding model is needed to generate numerical representations embeddings of the textual data. Popular options include sentence transformers, a library specializing in pre-trained sentence embedding models. OpenAI embeddings, offered by OpenAI's Application Programming Interface API. For generating high-quality embeddings. Fine-tune parameters. Distance metric used for similarity search. Popular choices include Euclidean distance measures the straight-line distance between 2 points in a multi-dimensional space. Cosine similarity measures the angle between two vectors, capturing their similarity in direction. Number of nearest neighbors to retrieve for each query. This parameter controls how many similar vectors are returned as search results. Challenges and fixes. Slow query performance can occur for large datasets. Optimizing the world index parameters, such as the number of partitions or the type of index structure, can significantly improve performance. Using a GPU-accelerated embedding model can speed up the embedding process and enhance overall query speed. Managing large datasets can be challenging. World offers sharding capabilities, enabling the distribution of the index across multiple machines or servers, effectively handling massive datasets. Cloud-based vector databases provide a robust and scalable solution for managing and querying large-scale vector datasets. These platforms often handle data storage, indexing, and search operations, relieving users from the burden of managing complex infrastructure. Langchain Community Vector Stores U-Search Summary. This document summarizes the U-Search vector database within the context of Langchain Community Vector Stores. It provides an overview of the functionalities, inputs, outputs, steps involved, prerequisites, fine-tuning parameters, and potential challenges and their corresponding fixes. Inputs. Text data to be indexed. Text data that is intended to be stored and searched in the U-Search vector database. This data can include documents, articles, code snippets, or any other text-based information. For instance, indexing customer reviews would allow you to search for similar reviews or find reviews related to specific products or services. Query text for searching. This represents the user's query that triggers a search within the indexed text data. The query could be a phrase, sentence, or even a single word. For example, searching for best headphones would retrieve documents relevant to that query. Outputs. Similar documents based on the query. The output of a U-Search search is a list of documents or text snippets that are most similar to the provided query. The similarity is determined based on the vector representations of the query and the indexed data. This can be used for tasks like finding relevant articles for a research paper, recommending products based on user preferences, or identifying potential duplicate content. Steps. Data is converted to vector embeddings. Text data is transformed into numerical representations, called vector embeddings. Each vector captures the semantic meaning of the text, allowing for efficient comparison and similarity calculations. This step utilizes embedding models like sentence transformers or OpenAI's text embeddings, which map text into high-dimensional vector spaces. Embeddings are stored in the database. The generated vector embeddings are stored in the U-Search database. U-Search offers efficient storage and retrieval of these vectors, making it suitable for large datasets. Query is converted to an embedding. The user's search query is also converted into a vector embedding, using the same embedding model as the one used for indexing the data. Database is searched for similar embeddings. U-Search performs a search operation, finding embeddings in the database that are most similar to the query embedding. This involves calculating the distance between the query embedding and the stored embeddings, with smaller distances indicating higher similarity. Prerequisites. U-Search library installed. Before using U-Search, you need to install the U-Search library. This can be done using the Python package manager pip install U-Search. USearch configuration file to set up and use USearch. A configuration file is required. This file specifies parameters such as the database location, indexing settings, and search parameters. Fine-tune parameters. Number of nearest neighbors to return. This parameter determines how many similar documents are retrieved in response to a search query. For example, setting it to 10 would return the top 10 most similar documents. Similarity metric. To use USearch provides various similarity metrics for comparing vectors. Common metrics include cosine similarity, Euclidean distance, and Manhattan distance. Choosing the right metric depends on the nature of the data and the desired search behavior. Challenges and fixes. Slow search speed. If the search speed is slow, particularly for large datasets, several optimizations can be applied. Use a more efficient search algorithm. Explore different search algorithms offered by USearch, such as approximate nearest neighbor and search algorithms, which can significantly improve search speed for large datasets. Optimize database parameters. Fine-tune database parameters like the number of shards or the index structure to optimize search performance based on the characteristics of the dataset. Memory issues with large datasets. Dealing with large datasets can lead to memory constraints. Use a smaller embedding model. Utilizing smaller embedding models that require less memory can help mitigate memory issues. Consider data chunking. Splitting large datasets into smaller chunks can allow for more efficient processing and reduce memory consumption. This involves indexing each chunk separately and then searching across all chunks for the relevant results. Langchain Community Vector Stores. WorldWorld. A description of the World Vector Database within the Langchain Community. This vector database is built on top of the open-source World library. World enables users to store and retrieve vector data efficiently. Inputs. Text data that needs to be embedded into vectors. This can include text from articles, books, documents, or any other form of textual content. For instance, you might have a collection of customer reviews that you want to analyze using World. Embeddings, which are numerical representations of the input text data. These embeddings capture the semantic meaning of the text and allow for efficient similarity comparisons. For example, a model trained to embed product descriptions might represent blue shirt and light blue shirt with similar vectors due to their close semantic relationship. Outputs.
A vector store object. This object provides an interface for interacting with the stored vectors. The vector store enables you to perform operations such as adding new vectors, searching for similar vectors, and retrieving specific vectors by their IDs. You can then use this vector store to power various downstream applications, like recommendation systems or question answering systems.
Steps. Load the embeddings into the World database. This step involves storing the vectors in the World server for efficient retrieval. During this process, World organizes the vectors in a way that optimizes search performance.
Search for similar vectors in Vault. This step involves querying the database with a given vector and retrieving the nearest neighbors based on the specified distance metric. For example, you could search for vectors similar to a user's query to find relevant documents in a large corpus.
Prerequisites. The World library needs to be installed on your system. This can be achieved using package managers like pip, as described in the World documentation. Installation instructions for World can be found at the World project's official documentation page, which will guide you through the process of setting up the World library on your system. The World server needs to be running. The World server is responsible for hosting the vector database and handling search queries. You can launch the Vault server using the command line instructions provided in the Vault documentation. The server will then be ready to accept requests from your applications. Fine-tune parameters. The number of dimensions of the vectors. This parameter specifies the size of the vector space, which is directly related to the complexity of the embeddings and the amount of information they can capture. For instance, a higher number of dimensions might allow for more nuanced semantic distinctions. But it also increases the computational cost of storing and searching vectors. The distance metric used for searching. This metric determines how similarity between vectors is calculated. Common distance metrics include Euclidean distance, cosine similarity, and Manhattan distance. Choosing the appropriate distance metric depends on the specific application and the properties of the embeddings. Challenges and fixes. Large embedding sizes can pose challenges when storing and searching vectors efficiently. One common solution is to use Vault sharding feature. Sharding divides the data into smaller partitions, allowing for more efficient storage and retrieval. This approach helps to mitigate the impact of large embedding sizes on search performance. Slow search performance can be a problem when dealing with large vector databases. To address this, you can optimize Vault configuration. This includes tuning parameters such as the number of shards, the size of the index, and the distance metric used for searching. These adjustments can significantly improve search performance and ensure efficient retrieval of relevant vectors. Langchain Community Vector Stores. Vectra is a cloud-based vector database service that enables storing and searching textual data using vector representations. It can be seamlessly integrated with Langchain, a powerful framework for building language-based applications. Inputs. Text data to be indexed. This refers to the textual content that you want to store in the vector database. It can be anything from news articles and blog posts to product descriptions and customer reviews. For example, you might want to index a collection of technical documentation to enable quick and efficient retrieval of relevant information. Query text to retrieve relevant information. This refers to the text that users will input to search the indexed data. For example, a user might enter a query like "What are the different types of machine learning algorithms?" to retrieve relevant documents from the indexed technical documentation. Outputs. Vectors representing text data. Vectra converts the input text data into numerical representations called vectors. These vectors capture the semantic meaning of the text and are used for efficient similarity search. For example, a vector representing a document on machine learning algorithms will be closer to a vector representing a document on supervised learning than a vector representing a document on financial news. Relevant documents based on query. Once a query is submitted, Vectra compares the vector representation of the query to the vectors of the indexed documents. Documents with vectors that are closer to the query vector are considered more relevant and are returned as results. This allows Vectra to retrieve documents based on their semantic similarity to the query, rather than simply matching keywords. Steps. Connect to Vectra application programming interface. This involves establishing a connection between your application and the Vectra service. This is typically done using a software library or API client that provides a standardized interface for interacting with the Vectra service. Upload text data and create index. Once connected to Vectra, you upload the text data you want to index. Vectra then processes this data and creates a vector index. This index allows for efficient searching of the data based on semantic similarity. For example, You might upload a collection of product reviews to create an index that allows users to search for products based on user feedback. Perform search based on query once the index is created. Users can submit queries to retrieve relevant documents. Vectra compares the vector representation of the query to the vectors in the index to find the most relevant documents. For example, a user might search for products that are comfortable and stylish based on user reviews in the index. Prerequisites. Vectra account. To use Vectra, you need to create an account on the Vectra platform. This will provide you with access to the service and the necessary credentials for authentication. Vectra Application Programming Interface Key. You will need a unique API key to authenticate your application with the Vectra service. This key is typically generated when you create your account and is used to grant your application access to the Vectra service. Python environment. Vectra can be integrated with Python applications using the Langchain library. This requires you to have a Python environment set up on your machine, along with the Langchain library installed. Fine-tune parameters. Dimensionality of vectors. This refers to the number of dimensions in the vector space used to represent the text data. Higher dimensionality can capture more complex relationships between words, but may require more computational resources. You can experiment with different dimensionality values to find the optimal setting for your use case. Similarity metric. This determines how Vectra measures the similarity between vectors. Common metrics include cosine similarity and Euclidean distance. The choice of metric can impact the relevance of search results. For example, cosine similarity is commonly used for text search as it focuses on the angle between vectors, which represents semantic similarity. Challenges and fixes. Authentication issues. This can occur when the API key is incorrect or when there is a problem with your account access. Ensure that you are using the correct API key and that your account is properly configured for accessing the Vectra service. Verify API key and account access. Double-check that you are using the correct API key and that your account is properly configured for accessing the Vectra service. This can involve verifying the API key in your application code and ensuring that your account is active and has the necessary permissions. Index creation errors. This can occur if the data format is incorrect or if there are issues with the Vectra service. Refer to the Vectra documentation for detailed information on the expected data format and any potential issues that might occur during index creation. Check data format and Vectra documentation. Review the Vectra documentation to ensure that your data is formatted correctly for index creation. You can also check the Vectra documentation for any known issues related to index creation and potential troubleshooting steps. Embedding function. This parameter specifies the text embedding model used to generate the numerical representations of your texts. For instance, you can use OpenAI's text embedding ADA002 model, which is known for its ability to generate accurate and robust embeddings. Collection name. This parameter indicates the name of the Vectra collection where your vectors will be stored. You need to create this collection beforehand, either using the Vectra UI or its API. Challenges and fixes. Error connecting to Vectra. This error can occur if your Vectra API key is incorrect, the collection you specified doesn't exist, or your internet connection is unstable. To resolve this, double-check the accuracy of your API key, verify the existence of the collection, and ensure a stable internet connection. Slow search times. Slow search performance might be due to improper indexing of your Vectra collection, a poorly optimized search query, or an inefficient embedding function. You can troubleshoot these issues by ensuring the collection is correctly indexed. refining your search query, and exploring the use of a different embedding function that may be more suitable for your specific task. Error: adding texts to the vector store. This error might indicate that your vector API key is incorrect. The collection doesn't exist, or your internet connection is unreliable. To address this, double-check your API key, verify the existence of the collection, and ensure a stable internet connection. Error: getting embeddings. This error might occur if your vector API key is incorrect, the collection you specified doesn't exist, or your internet connection is unstable. To resolve this, double-check the accuracy of your API key, verify the existence of the collection, and ensure a stable internet connection. Error: deleting texts from the vector store. This error might indicate that your vector API key is incorrect, the collection doesn't exist, or your internet connection is unreliable. To address this, double-check your API key, verify the existence of the collection, and ensure a stable internet connection. Error: getting metadata. This error might occur if your vector API key is incorrect, the collection you specified doesn't exist, or your internet connection is unstable. To resolve this, double-check the accuracy of your API key, verify the existence of the collection, and ensure a stable internet connection. Error: getting documents. This error might indicate that your vector API key is incorrect, the collection doesn't exist, or your internet connection is unreliable. To address this, double-check your API key, verify the existence of the collection, and ensure a stable internet connection. Error: loading the vector store. This error might indicate that your vector API key is incorrect, the collection doesn't exist, or your internet connection is unreliable. To address this, double-check your API key, verify the existence of the collection, and ensure a stable internet connection. Error: saving the vector store. This error might indicate that your vector API key is incorrect, the collection doesn't exist, or your internet connection is unreliable. To address this, double-check your API key, verify the existence of the collection, and ensure a stable internet connection. Error: clearing the vector store. This error might indicate that your vector API key is incorrect, the collection doesn't exist, or your internet connection is unreliable. To address this, double-check your API key, verify the existence of the collection, and ensure a stable internet connection. Error: searching the vector store. This error might indicate that your vector API key is incorrect, the collection doesn't exist, or your internet connection is unreliable. To address this, double-check your API key, verify the existence of the collection, and ensure a stable internet connection. Error: getting the similarity search function. This error might indicate that your vector API key is incorrect, the collection doesn't exist, or your internet connection is unreliable. To address this, double-check your API key, verify the existence of the collection, and ensure a stable internet connection. Error: getting the similarity search with score function. This error might indicate that your vector API key is incorrect, the collection doesn't exist, or your internet connection is unreliable. To address this, double-check your API key, verify the existence of the collection, and ensure a stable internet connection. Error: getting the max marginal relevance search function. This error might indicate that your vector API key is incorrect, the collection doesn't exist, or your internet connection is unreliable. To address this, double-check your API key, verify the existence of the collection, and ensure a stable internet connection. Error: getting the similarity search with filter function. This error might indicate that your vector API key is incorrect, the collection doesn't exist, or your internet connection is unreliable. To address this, double-check your API key, verify the existence of the collection, and ensure a stable internet connection. Error getting the similarity search with score and filter function. This error might indicate that your vector API key is incorrect. The collection doesn't exist, or your internet connection is unreliable. To address this, double-check your API key, verify the existence of the collection, and ensure a stable internet connection. Error getting the max marginal relevance search with filter function. This error might indicate that your vector API key is incorrect. The collection doesn't exist, or your internet connection is unreliable. To address this, double-check your API key, verify the existence of the collection, and ensure a stable internet connection. Error getting the similarity search with score and filter function. This error might indicate that your vector API key is incorrect. The collection doesn't. Langchain Community Vector Stores Vespa Store. Vector store that leverages the Vespa search engine for efficient and scalable vector similarity. Search. Inputs. Textual data to be indexed and searched. This could include documents, articles, code snippets, or any other text-based content. Configuration details for connecting to the Vespa cluster. This includes information like the cluster's IP address, port number, and authentication credentials. Outputs. Embeddings of the input text data, which are numerical representations capturing the semantic meaning of the text. These embeddings are used for similarity search. Results from searching the indexed data based on query embeddings. This includes a ranked list of relevant data points along with their similarity scores to the query. Steps. Creation of a Vespa cluster, which is a distributed search engine system. This step involves provisioning the necessary infrastructure and configuring the cluster. Storing the provided textual data in the Vespa cluster. This involves indexing the data and making it searchable. Generation of numerical embeddings for the text data using an embedding model. This model converts text into vector representations that capture semantic relationships, saving the generated embeddings in the Vespa cluster alongside the original data. This allows for efficient vector similarity search. Querying the Vespa cluster with new embeddings to retrieve relevant data based on semantic similarity. This involves finding the data points whose embeddings are most similar to the query embedding. Prerequisites. Installation of a Vespa cluster, which is a distributed search engine. It can be downloaded and installed from the official Vespa website. Installation of the Vespa SDK, which provides a set of tools and libraries for interacting with the Vespa cluster programmatically. This SDK enables you to manage the cluster, index data, and perform search queries. Fine-tune parameters. Choice of an embedding model, which determines how the text data is transformed into numerical embeddings. Different models can capture different aspects of the text's meaning. Selection of a similarity metric for measuring the closeness between embeddings. Common metrics include cosine similarity and Euclidean distance. Tuning of indexing parameters within the Vespa cluster. These parameters affect the efficiency and accuracy of the search process. This may include adjusting the number of shards, the indexing strategy, and the search query configuration. Challenges and fixes. Slow query performance can be encountered in cases with large datasets or complex search queries. To address this, optimizing the indexing parameters is important. This involves experimenting with different configurations to find a balance between indexing speed and search accuracy. Furthermore, leveraging Vespa's built-in query optimization features can significantly enhance the performance of complex searches. Vespa configurations can be complex, especially when dealing with advanced features or specific use cases. To navigate this, it's recommended to use Vespa's configuration tools. which provide a graphical interface for managing the cluster and its settings. Additionally, consulting Vespa's documentation offers comprehensive guidance on configuring the cluster and its components. Langchain Community Vector Stores Vespa Store Summary. None. A vector store that utilizes Vespa, a search engine renowned for its swiftness and scalability, for efficiently storing and retrieving data. Inputs. A dataset of information intended to be indexed within the Vespa vector store. This data can be in various formats, such as text documents, images, or audio files, depending on the specific use case and the capabilities of Vespa. Outputs. The indexed dataset, now stored in Vespa's vector store, ready to be retrieved or analyzed. This output represents the successful integration of the input data into the Vespa system, enabling efficient search and retrieval operations. Steps. Establishing a connection to a running Vespa instance, ensuring the vector store can interact with the search engine. This connection involves authentication and authorization to access the Vespa system and its resources. Indexing the provided dataset into Vespa's vector store. This step involves transforming the data into a format suitable for Vespa's indexing mechanism, assigning relevant metadata, and storing it in a manner that allows for efficient retrieval. Executing queries against the indexed data in Vespa. These queries can be based on specific search terms, semantic similarity, or other criteria, allowing users to retrieve relevant data from the vector store. Prerequisites. A running Vespa instance, which serves as the foundation for the vector store. This instance includes the necessary infrastructure and configuration to handle indexing, storage, and retrieval operations. A Vespa client library, which enables communication and interaction with the Vespa instance. This library provides the necessary application programming interface API to perform tasks like indexing, querying, and managing the vector store. Fine-tune parameters. Parameters related to the indexing process, including how the data is transformed, the specific metadata assigned, and the strategies employed for efficient storage within Vespa. These parameters can influence the performance and accuracy of search results. Parameters affecting the execution and behavior of queries. This includes factors like the search strategy, the criteria used for ranking results, and the specific parameters used to optimize query performance. Fine-tuning these parameters can significantly impact the quality and efficiency of retrieved data. Challenges and fixes. Issues establishing a connection between the vector store and the Vespa instance. Validating Vespa credentials. Ensuring that the vector store has the necessary access rights to connect to and interact with the Vespa instance. This could involve checking for correct usernames, passwords, and API keys, and addressing any potential authentication or authorization errors. Slow indexing performance, impacting the efficiency of adding data to the vector store. Optimizing Vespa's configuration, including settings related to indexing speed, resource allocation, and data partitioning. This can involve adjusting parameters like the number of index threads, the size of data segments, and the use of data compression techniques to improve indexing performance. Suboptimal query performance, resulting in slow or inaccurate retrieval of data. Fine-tuning query parameters, including the search strategy, the ranking criteria, and the use of query optimization techniques. This can involve adjusting parameters like the number of returned results, the relevance scoring mechanism, and the use of query filters to improve query performance and ensure accurate retrieval of relevant data. Langchain Community Vector Stores Viking DB config. VikingDB config is a configuration object for VikingDB. A vector database. VikingDB is a vector database that is optimized for storing and retrieving large amounts of data. It is designed to be highly scalable and performant. And it is well suited for use cases such as search, recommendation, and machine learning. Inputs. A list of embeddings to be stored. Embeddings are numerical representations of textual data that can be used to measure the similarity between different pieces of text. In the context of vector databases, embeddings are used to store and retrieve information based on its meaning rather than its literal text. Embeddings are typically generated by a machine learning model trained on a large corpus of text. A VikingDB connection object. A VikingDB connection object represents a connection to a VikingDB instance. It provides methods for interacting with the database, such as creating collections, adding embeddings, and querying the database. Outputs. A vector store object. A vector store object is an object that stores and retrieves vector data. It provides methods for adding and retrieving embeddings, as well as for searching the database based on similarity. Steps. Initialize a VikingDB connection. This involves establishing a connection to the VikingDB instance using the provided connection object. Create a VikingDB collection. A collection is a logical grouping of embeddings within a VikingDB instance. It allows users to organize and manage their embeddings in a structured way. Add embeddings to the VikingDB collection. This involves adding the embeddings to the specified VikingDB collection. The embeddings are stored in the database and can be retrieved later using the vector store object. Prerequisites. VikingDB installation. VikingDB can be installed either through Docker or through local installation. Docker installation provides a lightweight and portable way to run VikingDB without installing any dependencies on the host system. Local installation requires the user to install VikingDB directly on the host system. VikingDB connection string. The VikingDB connection string is a string that contains the information needed to connect to a VikingDB instance. This includes information such as the user, password, and host of the database. Fine-tune parameters. Dimension. The dimensionality of the embeddings. The dimensionality of the embeddings is the number of dimensions in each embedding vector. This is typically determined by the embedding model used to generate the embeddings. Collection name. The name of the collection to store the embeddings. The collection name is a user-defined name for the VikingDB collection. It is used to identify and access the collection. Challenges and fixes. Unable to connect to VikingDB. This issue might occur due to incorrect connection string, network connectivity issues, or access permission problems. To fix this, check the connection string to ensure it is correct. Also, verify the network connectivity to the database instance and make sure that the application has the necessary permissions to access the database. Error. Creating a VikingDB collection. This error might occur due to insufficient permissions, already existing collection with the same name, or incorrect collection configuration. To fix this, verify that the user has the necessary permissions to create collections. Ensure that the specified collection name does not already exist also. Check the collection configuration settings to make sure they are correct. Error. Adding embeddings to VikingDB. This error could happen due to incorrect embedding format, invalid collection name, or insufficient storage space in the database. To troubleshoot this, ensure that the embeddings are in the correct format expected by VikingDB. Verify that the specified collection name exists and is accessible. Lastly, check if the database has enough storage space to accommodate the new embeddings. Langchain Community Vector Stores vLite. A summary of the vLite vector store in the Langchain Community Vector Stores repository. Text data that is intended to be indexed and searched within the vLite vector store. This data could be anything from articles and documents to product descriptions or code snippets. A FICE index object, which acts as a container for the embedded vectors representing the text data. FICE provides various index types optimized for different search scenarios. A vLite vector store object that encapsulates the indexed text data and the FICE index, allowing for efficient querying and retrieval. The FICE index object, now populated with the embedded vectors derived from the text data. This index enables rapid similarity searches based on the stored vectors. The process begins by initializing the vLite vector store with a pre-existing FICE index object. This initialization establishes the foundation for storing and searching vectors within vLite. The text data is then added to the vLite vector store. This involves embedding the text data into numerical vectors using a suitable embedding model and storing these vectors within the FICE index associated with the vLite vector store. Once the text data is indexed, vLite allows you to perform similarity searches using the FICE index. The search process involves finding the most similar vectors within the FICE index to a given query vector, thus enabling efficient retrieval of relevant text data. FICE library installed. The FICE library provides efficient algorithms for searching through large datasets of vectors, making it an ideal choice for vector store implementations. The FICE CPU package can be installed using the pip command. This package provides the necessary functionality for creating and using FICE indexes on a CPU. Text data to be indexed. This data could be articles, documents, product descriptions, or any other text content that you wish to store and search within the vLite vector store. The text data should be preprocessed before being indexed. Preprocessing typically involves steps like cleaning, tokenization, and normalization to improve the quality of the embeddings and enhance search accuracy. FICE index type. The FICE library offers a range of index types, each optimized for different search scenarios. Selecting the appropriate index type is crucial for achieving optimal search performance. For example, you might choose an index type that prioritizes speed for real-time applications or one that emphasizes accuracy for precise search results. Dimensionality of vectors. The dimensionality of the vectors represents the number of dimensions used to represent the text data. This parameter influences the complexity of the search space and can impact search performance. Selecting an appropriate dimensionality involves considering factors like the complexity of text data and the computational resources available. Large datasets may not fit in memory. This scenario poses a challenge for vLite because it relies on in-memory storage. To address this, disk-based FICE indexes or alternative vector stores that support persistent storage can be used to accommodate larger datasets. Disk-based FICE indexes enable the storage of large datasets on disk, allowing for efficient retrieval even when the data exceeds available memory. Other vector stores, such as Chroma or VV8, are designed to handle large datasets and may be more suitable for this purpose. Slow search performance. While FICE is known for its efficiency, search performance can still be a concern, particularly with large datasets. To optimize search performance, it's essential to choose appropriate FICE index parameters, such as the index type and dimensionality, and to consider strategies for indexing and querying the data. Optimizing FICE index parameters involves carefully selecting the index type and dimensionality to align with the specific search requirements. This may entail experimentation to determine the optimal configuration. Techniques like batch indexing and query optimization can also enhance search performance. Langchain Community Vector Stores vLite Summary. A vector store designed for storing and retrieving vectors in a lightweight way using vLite. vLite is a lightweight library for storing and retrieving vectors. It is designed to be efficient and scalable, making it suitable for use in a wide range of applications. This vector store can be used in various applications, like search engines, recommender systems, and question answering systems. Inputs. Text data for embedding. This refers to the textual information that is fed into the vector store. The text data is first transformed into numerical representations, called embeddings, which capture the semantic meaning of the text. Outputs. Embedded vectors. These are the numerical representations of the input text data. They capture the semantic meaning of the text, allowing for efficient similarity-based search. Text data for retrieval. Once the user provides a query, the vector store retrieves text data that is semantically similar to the query. The retrieved text data is presented to the user as relevant results. Steps. Text data is embedded using a suitable model. This step involves using a pre-trained model, such as a transformer model, to convert text into numerical representations or embeddings. These models learn complex relationships between words and phrases, allowing for the creation of semantically meaningful embeddings. Embedded vectors are stored in vLite. vLite stores the generated embeddings efficiently and allows for fast retrieval based on similarity. This enables efficient search and retrieval of relevant information from the vector store. Retrieval is performed by searching for the closest vectors in vLite based on a query. When a user enters a query, the vector store transforms the query into an embedding using the same model used for embedding text data. Then, it searches for the closest embeddings in the vLite storage based on similarity. The text data associated with these closest embeddings is retrieved and presented to the user as relevant results. Prerequisites. Installation of vLite. vLite is a Python library that needs to be installed before using this vector store. The installation can be done using the pip package manager. Fine-tune parameters. Similarity metric for vector search. The choice of the similarity metric affects how the vector store determines the closeness between the query embedding and the stored embeddings. Different metrics, like cosine similarity or Euclidean distance, can be used depending on the specific application and the desired level of precision. Dimensionality reduction technique. Dimensionality reduction techniques are used to reduce the number of dimensions in the embedded vectors, which can improve efficiency and reduce computational complexity. Various techniques, such as principal component analysis (PCA) or T-distributed stochastic neighbor embedding (TSNE), can be used depending on the specific dataset and application requirements. Challenges and fixes. Handling large datasets. Large datasets can pose challenges in terms of storage and retrieval efficiency. To address this, chunking or sampling techniques can be used to divide the data into smaller manageable units, enabling faster processing and retrieval. Maintaining high retrieval accuracy. Achieving high retrieval accuracy requires careful selection of embedding models and similarity metrics. Experimenting with different model architectures and similarity metrics allows for finding the best combination that maximizes retrieval accuracy for the specific application and dataset. Langchain Community Vector Stores vv8 Summary. vv8 is a vector database that is used in Langchain for storing and retrieving vector embeddings. Vector embeddings are numerical representations of text data, allowing for efficient semantic search and similarity calculations. VV8 enables Langchain to manage and query large datasets of text documents by transforming them into vector embeddings and storing them in a way that allows for fast and accurate retrieval. Based on semantic similarity. Inputs. Text data that is fed into VV8, such as articles, documents, or any textual information. This data is then converted into vector embeddings for storage and retrieval. Outputs. Vector embeddings, which are numerical representations of the input text data, stored in VV8. Retrieved documents based on similarity searches against the stored embeddings using a query. Steps. A VV8 client is created to connect to the VV8 database. This is the interface that allows Langchain to interact with the vector database. Documents are indexed into VV8, where they are converted into vector embeddings using a chosen embedding model and stored for later retrieval. Queries are performed against the stored vector embeddings in VV8. This involves comparing the query with the stored embeddings based on semantic similarity. Retrieving the most relevant documents. Prerequisites. VV8 installation. Meaning that VV8 needs to be installed and running on your system to utilize it with Langchain. The installation process involves setting up the database and configuring it for use. Install VV8 on your system using the provided installation instructions for your operating system. This step ensures that the VV8 database is accessible and ready for interaction with Langchain. Langchain installation. Ensuring that Langchain is installed in your Python environment using pip. Langchain provides the framework and components for interacting with vector databases like VV8. Install Langchain using the command pip install Langchain in your terminal. This will install the necessary packages and make Langchain available for use in your Python code. Fine-tune parameters. VV8 client configuration involves specifying the connection details for the VV8 database, such as the host address, port, and other relevant information. This configuration determines how Langchain interacts with the VV8 database.
Vectorization model, which determines how the text data is converted into vector embeddings. Choosing an appropriate vectorization model is crucial for achieving accurate semantic similarity comparisons in the search process.
Challenges and fixes. Connection issues may arise when trying to connect to the VV8 database. This could be due to incorrect settings, network issues, or other problems. Check the connection settings in the VV8 client configuration. Verify that the host address, port, and other parameters are correct and that the database is accessible. Index performance. Referring to how efficiently documents are converted into vector embeddings and stored in VV8. Poor index performance can lead to slow indexing times and affect the overall speed of the search process. Optimize indexing parameters, such as batch size, indexing strategy, and other options, to improve index performance. Experiment with different settings to find the optimal configuration for your specific use case. Search accuracy refers to the quality of the results returned from searches based on semantic similarity. Poor search accuracy can lead to irrelevant or inaccurate documents being returned. Fine-tune the vectorization model. Experimenting with different embedding models or adjusting parameters within the chosen model to improve the quality of the vector embeddings and enhance search accuracy. Langchain Community Vector Stores VikingDB config. This document describes how to configure Langchain to interact with VikingDB, a vector database. Inputs. VikingDB connection details are essential for Langchain to connect and interact with the database. These details typically include the database host, port, username, password, and database name. Data that needs to be indexed within VikingDB, such as text documents, images, or other types of data. The data will be transformed into vector representations and stored in the database for efficient search and retrieval. Outputs. The VikingDB index is a structured representation of the indexed data within the database, enabling efficient searching and retrieval of relevant information based on vector similarity. Steps. Establishing a connection to VikingDB using the provided connection details is the first step in the process. This allows Langchain to access and interact with the database. Uploading data to the database involves converting the data into vector representations and storing them within VikingDB. This process allows for efficient search and retrieval based on vector similarity. Creating an index on the uploaded data within VikingDB involves organizing the data in a structured way. This enables fast and efficient searches based on vector similarity. Prerequisites. VikingDB installation is required before interacting with the database, ensuring that the necessary software and libraries are available for connecting and managing data within the database. VikingDB Application Programming Interface API credentials are needed for Langchain to authenticate with the database and perform operations such as data upload, indexing, and querying. Fine-tune parameters. Index parameters are settings that can be adjusted to optimize the performance and accuracy of searching within the database. These parameters can include settings related to the indexing algorithm, dimensionality reduction techniques, and other factors that influence the quality of the search results.
The embedding model is used to convert the input data into vector representations that are suitable for storage and search within the database. Choosing the right embedding model can have a significant impact on the accuracy and efficiency of the search process.
Challenges and fixes. Challenge 1. Data size exceeding VikingDB capacity can occur when the amount of data to be indexed is too large for the available database resources. Fixes to Challenge 1. Data partitioning involves dividing the data into smaller subsets that can be stored and indexed independently, reducing the overall workload on the database. Scaling VikingDB involves increasing the hardware resources available to the database, such as adding more storage or processing power to handle larger datasets. Challenge 2. Slow query response times can occur when the database is under heavy load, the index is not optimized, or the search queries are complex. Fixes to Challenge 2. Optimizing the index configuration can involve adjusting settings such as the number of dimensions used for vector representation, the indexing algorithm, and other factors that can affect search speed. Upgrading VikingDB can involve moving to a more powerful hardware configuration, improving the database's capacity to handle large datasets and complex queries. Langchain Community Vector Stores Yellowbrick. A vector store based on Yellowbrick, a Python library for machine learning, particularly focused on data exploration and visualization. Yellowbrick provides tools to visualize the process of building machine learning models, aiding in the selection and tuning of the right model for your task. This vector store utilizes Yellowbrick's capabilities to embed documents, allowing for efficient retrieval of similar documents based on semantic content. Inputs: a list of text documents or embeddings that you want to store and search. These documents can be plain text, such as articles or product descriptions, or they can be pre-computed embeddings representing the semantic meaning of the text. The vector store will use these inputs to create a searchable index of your documents. The Yellowbrick model to use for embedding the documents, such as TF-IDF transformer or count vectorizer. These models transform the text documents into numerical vectors, capturing the semantic relationships between words and phrases within the text. You can choose the model based on the nature of your data and the desired level of semantic representation. Outputs. A vector store object that can be used to search and retrieve documents based on similarity. This object provides methods to add documents, search for similar documents, and access the underlying data structures. The similarity search functionality is based on the embedding vectors, allowing you to retrieve documents that are conceptually similar to a given query. Steps. Initialize the Yellowbrick vector store with the chosen model. This step involves setting up the vector store with the desired embedding model and any associated configuration parameters. Add documents to the vector store using the add method. This method takes a list of documents or embeddings as input and adds them to the vector stores. Index. The documents are processed using the chosen embedding model to create corresponding vector representations. Search for similar documents using the similarity search method. This method takes a query document or embedding as input and returns a list of documents from the vector store that are most similar to the query, based on the semantic relationships captured by the embedding vectors. The returned list of documents is ranked based on their similarity scores, allowing you to prioritize the most relevant results. Prerequisites. Yellowbrick library installed. Pip install Yellowbrick. The Yellowbrick library is essential for creating and using the vector store, as it provides the underlying embedding models and functionalities. You can install it using the pip package manager. Scikit-learn library installed. Pip install scikit-learn. The scikit-learn library is required as a dependency for Yellowbrick, providing a wide range of machine learning algorithms and utilities that are leveraged by the vector store. Ensure that you install scikit-learn before installing Yellowbrick. Fine-tune parameters. Model. The Yellowbrick model used for embedding. This parameter allows you to specify the embedding model that will be used to transform your documents into vector representations. You can choose from various Yellowbrick models, such as TF-IDF transformer, count vectorizer, or any custom embedding model you may have defined. Embedding function. A function to extract embeddings from documents if not using a predefined Yellowbrick model. This parameter provides flexibility if you have a custom embedding method that is not directly supported by Yellowbrick. You can define a function that takes a document as input and returns a vector representation, and pass it to the vector store during initialization. Challenges and fixes. Error handling for invalid input data or missing Yellowbrick dependencies. Ensure correct installation of Yellowbrick and scikit-learn libraries. Check for data type consistency and validity. If you encounter errors related to missing dependencies or invalid input data, review the installation instructions and ensure that the required libraries are installed correctly. Check the data format and types to make sure they comply with the expectations of the vector store and the embedding model. Performance bottlenecks for large datasets. Consider using a more efficient embedding model or data preprocessing techniques. Implement data sharding or distributed vector storage. For large datasets, the performance of embedding and search operations can be a concern. To mitigate this, explore using more efficient embedding models that are optimized for large-scale data. You can also consider preprocessing your data to reduce its size and complexity, potentially by removing irrelevant information or applying dimensionality reduction techniques, in cases where a single machine cannot handle the entire dataset. You can consider data sharding or using distributed vector storage solutions to distribute the data and processing across multiple machines. These techniques can improve performance and scalability for very large datasets. Langchain Community Vector Stores vLite. This vector store is an in-memory vector store implementation, which is designed for lightweight use cases. It can be used to store and retrieve vectors in memory. This is useful for applications where speed and low memory footprint are important. But it is not suitable for applications that need to store very large amounts of data. Inputs. Text data refers to the text that will be embedded and stored in the vLite vector store. The text data can be in any format, such as plain text, HTML, or JSON. A real-world example would be a collection of news articles, product descriptions, or customer reviews. An embedding function is used to convert the text data into a numerical representation that can be stored and compared. The embedding function maps each text input to a vector of numbers, representing its meaning and semantic relationships. Common examples include OpenAI's ADA or text embedding ADA 002 embedding models. Outputs. The output of vLite is a vector store, which is a data structure that stores the embeddings of the text data. This vector store can then be used to perform similarity search, retrieve relevant text data based on query embeddings, or analyze the relationships between different pieces of text data. Steps. To use vLite, you must first initialize it with the text data and the embedding function. This involves passing the text data and the embedding function to the vLite constructor. Next, add embeddings to the vLite vector store. This is done by calling the add method on the vLite object. This method takes the text data and the corresponding embedding as input. Finally, you can retrieve embeddings from the vLite vector store by using the similarity search method. This method takes a query embedding as input and returns a list of embeddings from the vector store that are similar to the query embedding. Prerequisites. Langchain is a Python library that provides a framework for building and deploying language models. Langchain provides a number of tools and components that make it easy to work with language models, including vector stores, http://Langchain, read the docs, ION-latest. An OpenAI API key is required to use the OpenAI embedding models, such as ADA or text embedding ADA 002. The key can be obtained from the OpenAI website. https platform, OpenAI.com account API keys. Fine-tune parameters. The embedding function parameter is used to specify the embedding model that will be used to convert the text data into numerical vectors. The embedding dimension parameter specifies the size of the embedding vectors that will be generated by the embedding function. Challenges and fixes. The main challenge of using vLite is that it is an in-memory vector store, which means that it can only store as much data as can fit in the available memory. This can be a problem for large datasets. Disk-based vector stores, such as FAISS or Chroma, can be used to store large datasets. These vector stores store the data on disk, which allows them to handle much larger datasets than in-memory vector stores. Performance issues can arise when embedding large datasets or performing similarity searches on a large number of embeddings. Using a GPU-accelerated embedding function can significantly improve performance. This can be done by using a GPU-enabled embedding model or by using a GPU-based embedding library, such as FAISS. Langchain Community Vector Stores VikingDB Summary. A vector database that allows efficient searching and retrieval of similar data points based on their vector representations. A vector database stores data as numerical representations called vectors, enabling efficient similarity searches by comparing the distances between vectors. This is useful for tasks like finding similar documents, images, or other data based on their content. Inputs: text data that needs to be indexed and stored in the vector database. This data can be in various formats like text documents, articles, or even code snippets. Metadata associated with the text data. Metadata is additional information about the data, such as its author, creation date, or other relevant tags. This metadata can be used to filter and refine search results. Outputs: similar text documents based on a given query vector. When you provide a query vector, the vector database retrieves documents that have similar vectors, effectively finding documents that are conceptually similar to the query. Metadata associated with the retrieved text documents. The retrieved documents come with their corresponding metadata, providing additional context and information about the retrieved results. Steps: create a Viking DB client object. This is the first step, and it involves establishing a connection to the Viking DB service using the Python client library. Index text data and its metadata in the vector database. After creating the client, the next step is to index the text data into the vector database. This involves converting the text data into vector representations and storing them along with their associated metadata. Perform similarity searches based on a query vector. The user provides a query vector that represents the desired search criteria. The vector database then compares this query vector with the indexed vectors to find similar documents. Retrieve relevant text documents and their associated metadata. Finally, the vector database returns the retrieved documents along with their associated metadata, providing relevant results based on the query. Prerequisites: install Viking DB Python client. This involves installing the necessary libraries using the pip package manager. Pip install Viking DB. Create a Viking DB account and obtain an application programming interface API key. This involves signing up for a Viking DB account, which provides access to the vector database service. An API key is necessary to authenticate with the service and perform operations. Fine-tune parameters. Vectorization model: choose a suitable model for encoding text into vectors. This involves selecting a vectorization model, such as sentence transformers, that effectively captures the semantic meaning of the text. Indexing parameters: optimize indexing parameters for efficient search and retrieval. This step involves fine-tuning the indexing parameters, such as the dimension of the vectors or the indexing algorithm, to ensure optimal performance and accuracy for search operations. Challenges and fixes. Challenge 1: unable to connect to the Viking DB service. This can occur due to incorrect application programming interface API key, wrong connection parameters, or network issues. Fixes to challenge 1: verify API key and connection parameters. Ensure that the API key and connection parameters are correct and that the Viking DB service is accessible. Challenge 2: indexing or search operations fail. This can happen due to network connectivity problems, data format incompatibility, or incorrect indexing parameters. Fixes to challenge 2: check network connectivity. Ensure data format compliance, and review indexing parameters. Verify network connectivity. Ensure that the data format is compatible with Viking DB. And check the indexing parameters to ensure they are correctly configured. Langchain Community Vector Stores Vector Summary Config. This is a description of the Langchain Community Vector Stores Vector, which is a vector store that utilizes vector for storing and retrieving embeddings for large language models. This enables efficient retrieval of pertinent information using embeddings, which is beneficial for building robust question answering systems, semantic search engines, and more. Inputs: text data that is to be embedded. For example, you might feed in a document or a collection of documents that you want to search through later. Embeddings for text. These are numerical representations of the text that capture its semantic meaning. You might obtain these embeddings from a pre-trained model or generate them yourself. Outputs: embeddings of text. These are the numerical representations of the text that you inputted. They can be used for searching or other downstream tasks. Relevant documents based on a query. When you provide a query, the vector store will return the documents that are most similar to it based on the embeddings. Steps. The process begins by embedding the text data using a selected embedding model. This model transforms text into numerical representations. Following the embedding process, the embeddings, along with the corresponding text, are stored within the vector database. This database efficiently manages and stores the embeddings for future retrieval. To retrieve relevant documents, a query is used. This query is also embedded using the same model as before. The vector store then finds documents whose embeddings are most similar to the query embedding, based on the chosen similarity metric. Prerequisites: vector account is required to use the vector store. You will need an account on the vector platform to store and retrieve your embeddings. Application Programming Interface Key is needed to interact with the vector API. This key enables you to access Vector's services programmatically. Fine-tune parameters. The embeddings model is a key parameter that determines how the text is converted into numerical representations. You can choose from various models, each with its strengths and weaknesses. For example, you might use a model optimized for understanding scientific text or a model trained for general-purpose text understanding. The similarity metric defines how the vector store measures the similarity between different embeddings. Different metrics can lead to different results, so it is important to choose a metric that is appropriate for your task. For instance, you might choose a metric that focuses on capturing semantic similarity, or a metric that considers the overall similarity between vectors. Challenges and fixes. Slow query response time can occur when searching through a large dataset. This challenge can be addressed by optimizing the query parameters and applying filtering techniques to reduce the search space. For example, you might restrict your search to a specific time range or a particular set of documents. Optimize query parameters and use filtering to reduce the search space. For instance, you can refine your queries by including keywords or phrases to narrow down the search results. Or you can specify a specific time range to focus on relevant documents. High embedding cost can be a concern, especially when dealing with massive amounts of text. You can address this by exploring cost-effective embedding models, such as those designed for efficient processing, and adjusting the embedding frequency. For example, you might choose to embed documents less frequently, perhaps only when they are updated or modified. Explore cost-effective embedding models and adjust the embedding frequency. For instance, you might investigate models that offer a good trade-off between accuracy and computational cost. You could also adjust the embedding frequency by only embedding new documents or those that have been significantly updated. ZEP Vector Store Summary. ZEP Vector Store is a vector database that stores and retrieves embeddings for use in text-based applications. For example, you can use ZEP Vector Store to store and retrieve embeddings of documents, code, or other text data. and then use those embeddings to perform tasks such as semantic search, question answering, and text summarization. Inputs: text data to be indexed and retrieved. This includes the text content itself, which can range from short phrases to entire documents. Metadata for the text data, such as the source or author. Metadata provides additional context and information about the text data, making it easier to organize, filter, and retrieve. For example, you might include metadata such as the document's title, author, publication date, or URL. Outputs: embeddings of the text data. These are numerical representations of the text data that capture its semantic meaning. Embeddings are typically high-dimensional vectors that can be used to compare and search for similar text data. Search results for text queries. When you query the vector database with a text query, ZEP Vector Store returns a list of text documents that are most similar to the query based on their embeddings. This is often referred to as semantic search, as the search engine considers the meaning of the query and the text data, rather than just matching keywords. Steps: initialize the ZEP Vector Store with an existing Zilli Milvus collection or create a new one. Milvus is an open-source vector database that stores and manages vectors efficiently. By initializing with an existing collection, you can leverage the pre-indexed data. If you create a new collection, you can define its structure and parameters, add text data and metadata to the vector store. This step involves converting the text data into embeddings and storing them in the vector database, along with the associated metadata. Retrieve embeddings for text data by providing the document IDs. After the text data is indexed, you can retrieve its embeddings using its unique identifier, known as the document ID. Search for relevant text data based on a query using similarity search. This involves comparing the query's embedding with the embeddings of all the documents in the vector database. ZEP Vector Store returns the documents with the highest similarity scores, meaning those that are most semantically similar to the query. Prerequisites: Zilli Milvus database, a high-performance vector database, is necessary. Install Milvus by following the instructions on the official documentation at https://milvus. io-docs install Milvus. ZEP Vector Store Library, a Python library that provides an interface for interacting with Milvus for vector storage and retrieval. Install ZEP Vector Store using pip install ZEP Vector Store. Fine-tune parameters. Similarity metric, a function that calculates the similarity between two vectors. Different metrics emphasize different aspects of the data. Cosine similarity calculates the cosine of the angle between two vectors. This is a common choice for semantic search as it considers the overall direction of the vectors, rather than just their magnitude. Euclidean distance calculates the straight line distance between two vectors. This is another common choice for vector similarity calculations, but it can be less robust to outliers than cosine similarity. Index type, which determines how the vector database stores and retrieves embeddings. Different index types offer different trade-offs in terms of performance, storage efficiency, and search accuracy. Flat index stores all embeddings in memory and performs a brute force search for similar vectors. This is the simplest and most straightforward index type, but it can be slow for large datasets. IVF flat index uses a technique called inverted file indexing to group similar embeddings together. This allows for faster search performance than flat indexing, as the database only needs to search through a smaller subset of embeddings. Challenges and fixes. Slow query performance for large datasets can occur because it takes time to calculate similarity. Scores for all vectors in the database. Optimize Milvus configuration and index type. For large datasets, it may be necessary to use a more efficient index type, such as IVF flat. You can also optimize the Milvus configuration parameters, such as the number of partitions and the number of shards, to improve query performance. Limited integration with other Langchain components can limit its flexibility. Use custom integrations or adapters to connect with other Langchain tools. For example, you can create a custom adapter that allows you to use Zep Vector Store with Langchains. Conversational AI tools. Langchain Community Vector Store's Annoy Dependable Annoy Import. Annoy Vector Store is a vector database that leverages Annoy library for efficient similarity search, and is a part of the Langchain Community library. Annoy Vector Store provides an efficient method to store and retrieve vectors based on their similarity to a query vector. This is particularly useful in applications like recommendation systems, document search, and image retrieval. Inputs. Data for storing vectors and their associated metadata. The input data consist of vectors representing the items to be stored and their corresponding metadata, which provides additional information about each item. For example, in a document search application, the vectors could represent the embedding of the document text, and the metadata could include the document title, author, and publication date. Annoy's parameters, including number of trees, dimension of the vectors, metric used for distance calculation. Annoy's parameters are crucial for optimizing the performance of the vector database. The number of trees determines the trade-off between search speed and accuracy. A higher number of trees results in more accurate search results but also requires more time to perform searches. The dimension of the vectors defines the number of features used to represent each item. The metric specifies the distance function used to calculate the similarity between vectors. Common metrics include cosine similarity and Euclidean distance. Outputs. Vector store object, allowing for operations like add, similarity search, and retrieval. The output is a vector store object that provides the necessary API for interacting with the stored vectors. This object allows you to add new vectors to the store, perform similarity searches, and retrieve vectors based on their metadata. Steps. Initialize Annoy Vector Store with Annoy's parameters. The first step is to initialize the Annoy Vector Store object with the desired parameters, including the number of trees, vector dimension, and distance metric. Add vectors and associated metadata to the store. Once the Annoy Vector Store object is initialized, you can add vectors and their associated metadata to the store. This process involves converting the input data into a format compatible with Annoy and storing it in the database. Perform similarity searches using Annoy's search functions. The primary function of the Annoy Vector Store is to perform similarity searches. This involves providing a query vector and retrieving the most similar vectors from the store based on the chosen distance metric. Prerequisites. Annoy library installed. Annoy library is a fast, efficient library for approximate nearest neighbor search. It is essential for the Annoy Vector Store to function correctly. Pip install Annoy. Installing the Annoy library is a simple process using the pip package manager. This command will download and install the necessary Annoy packages and dependencies on your system. Fine-tune parameters. Number of trees controls the trade-off between search speed and accuracy. The number of trees is a critical parameter that influences the search performance of Annoy. Increasing the number of trees improves accuracy but also increases search time. In real-world applications, the number of trees is typically chosen based on the desired balance between speed and accuracy. considering factors like the size of the dataset and the criticality of search precision. Metric: choose the appropriate metric for distance calculation, e.g., cosine. Euclidean. The choice of distance metric is crucial for determining the similarity between vectors. Cosine similarity is commonly used for measuring the angle between two vectors, while Euclidean distance calculates the straight-line distance between 2 points in space. The appropriate metric depends on the specific application and the characteristics of the data. Challenges and fixes. Annoy is known to be slow for large datasets. Annoy's performance can degrade for large datasets due to the computational complexity of nearest neighbor search. This limitation becomes more pronounced as the dataset size increases, leading to longer search times. Consider using other vector databases for larger datasets. For handling large datasets, it is recommended to explore other vector databases that are specifically optimized for scalability, such as FICE or HNSW. These databases often employ different indexing techniques and algorithms that are more efficient for large-scale similarity search. Potential issues with serialization and deserialization for large datasets. Serialization and deserialization are processes of converting data between different formats, such as converting an object to a byte stream for storage or transmission. In the context of Hanoi vector store, serialization and deserialization can become problematic for large datasets, potentially leading to performance bottlenecks. Explore alternative serialization methods or use a different vector store. To address these issues, you can investigate alternative serialization methods that are more efficient for large datasets, such as using a binary format or employing specialized libraries for serialization. Alternatively, using a different vector store designed for handling large datasets might be a more practical solution. Langchain Community Vector Stores FICE Dependable FICE Import. FICE Facebook AI Similarity Search is an open-source library for efficient similarity search and clustering of large datasets. Dependable FAISS import is a utility to address a common issue in FAISS: inconsistencies in import behavior due to versioning and environment setups. This method ensures a consistent and predictable way of using FICE inputs, a FAISS index that has been previously built. This index contains a collection of data points and their corresponding embeddings, typically generated by a vector embedding model. A list of embeddings that you want to search against. These are the vectors representing the data points that you want to find similar counterparts for in the FAISS index. Outputs: a list of the closest matches from the FAISS index to the input embeddings. The output will contain a list of the data points from the index that are most similar to the input embeddings based on their vector representations. The corresponding distances between the input embeddings and the retrieved matches. The output will also contain a list of the distances between each input embedding and its corresponding match. This distance represents the similarity, with smaller distances indicating higher similarity. Steps: install FAISS using pip. Specifying a specific version to avoid import issues. You can specify the desired version of FAISS when installing it using pip. This ensures that you are using the exact version that you need and minimizes the risk of unexpected behavior caused by version incompatibilities. Import FAISS from the specified version using the from version import format. This import statement ensures that you are importing the FAISS module from the specific version you installed using pip. This helps to maintain consistency across different environments and avoids issues related to import paths or version mismatches. Prerequisites: a local installation of Python. This is necessary as FAISS is a Python library and requires a Python environment to run. Python version 3.6 or higher. Python version 3.6 or higher is required for FAISS. FAISS installed on the system. You need to install FAISS on your system using pip. This can be done by installing the appropriate version of FAISS using pip install FAISS CPU for CPU BASED implementations or pip install FAISS GPU for GPU accelerated implementations. Fine-tune parameters. The specific version of FAISS to use. The specific version of FAISS you use can impact performance and functionality. It's important to choose a version that is compatible with your other libraries and dependencies that provides the features you need. The number of nearest neighbors to retrieve. This parameter specifies how many of the closest matches from the FAISS index you want to return as results. A larger number of nearest neighbors will provide a more comprehensive set of potential matches, but may increase search time. Challenges and fixes. Import errors or inconsistencies in FAISS behavior. It is important to ensure that FAISS is imported consistently across different environments. By specifying the version explicitly and using the from version import format, you can avoid import issues related to version mismatches or conflicting paths. Version conflicts with other libraries or dependencies. Version conflicts can occur when different libraries have conflicting dependencies on different versions of FAISS. To resolve this, you can install a specific version of FAISS that is compatible with all other libraries in your project. Langchain Community Vector Stores. Zep Vector Store. A vector store implementation based on the Zep library, designed to enable efficient vector search and similarity matching using the Zep server. Zep Vector Store leverages the Zep server's capabilities to store and retrieve vectorized representations of data, enabling applications like document search, recommendation systems, and question answering. Inputs. Textual data, raw text content that will be transformed into vectors and stored in the vector store. For example, this could include articles, blog posts, product descriptions, or any other textual information. Metadata. Additional information associated with the textual data, such as author, publication date, topic, or any other relevant context. Metadata can enhance search relevance by providing more insights into the content. Outputs. Embeddings. Numerical representations of the textual data, created using embedding models e.g. BERT, sentence transformers. These embeddings capture semantic meaning and relationships between words, allowing for more accurate similarity comparisons. Search results. The output of a search operation, containing a list of documents or items ranked based on their similarity to the query. Search results provide the most relevant content matching the user's intent. Steps. Initialization. The Zep Vector Store is initialized by providing the Zep server URL and the database name. This step establishes a connection to the Zep server and prepares the vector store for data ingestion. For example, you might initialize the vector store with the URL http://myspserver.com and the database name my documents. Data ingestion. Textual data along with its associated metadata is ingested into the Zep server, creating a vector index. During ingestion, the data is converted into numerical embeddings, which are then stored within the Zep server's database, allowing for efficient search and retrieval. For instance, you could ingest a collection of scientific articles with their respective authors, publication dates, and keywords. Embedding generation. The ZEP vector store utilizes embedding models to generate numerical representations of the textual data. These embeddings capture semantic relationships between words and phrases, enabling similarity search based on meaning rather than just lexical matching. The chosen embedding model should be suitable for the type of data and the intended use case. For example, if you are dealing with scientific articles, you might choose a model specialized in scientific literature. Search. The vector store performs a similarity search based on query embeddings retrieved from the query text. This search operation leverages the vector index to efficiently find documents or items most similar to the query, allowing users to discover relevant content based on their search intent. For instance, a user might search for machine learning algorithms, and the vector store would return a list of articles or documents relevant to this topic. Prerequisites. ZEP server. A running instance of the ZEP server is required, configured with appropriate database settings. The ZEP server acts as a backend for the vector store, handling data storage, indexing, and search operations. For example, you might need to configure the ZEP server to use a specific database engine and define access permissions. ZEP library. The ZEP Python library must be installed within the environment to interact with the ZEP server and perform vector store operations. This library provides the necessary functions for data ingestion, search, and other vector store management tasks. You can install the ZEP library using a package manager like pip install ZEP. Fine-tune parameters. ZEP server configuration. The ZEP server configuration determines the connection details, such as the server URL, database name, and any authentication credentials. Optimizing the server configuration can improve performance and stability. For example, you can configure the database engine, specify storage settings, and adjust network parameters. Indexing parameters. Indexing parameters control how the vector index is built and optimized for search. These parameters can include options for dimensionality reduction techniques, index structure, and search algorithms. For example, you might adjust the number of dimensions used for embedding vectors, select a specific indexing algorithm, and choose the appropriate search algorithm for your use case. Challenges and fixes. Server connectivity issues. Connection errors between the client ZEP vector store and the ZEP server can occur due to network problems, server outages, or misconfigured connection settings. To resolve these issues, verify network connectivity, confirm server availability, and reconfigure the connection settings if needed. In real-world scenarios, you might need to check for firewall restrictions, ensure the server is reachable, and double-check the provided URL and port numbers. Indexing performance degradation. Slow indexing or search operations can be caused by various factors, including inefficient indexing parameters, high dimensionality of embeddings, or unoptimized embedding models. To address these issues, optimize indexing parameters, e.g., adjust indexing algorithms, experiment with different dimensionality reduction techniques, consider using more efficient embedding models, and explore alternative indexing strategies for improved performance. In real-world scenarios, you might need to analyze the data distribution, optimize embedding model selection, and adjust the index structure based on the specific characteristics of your data. Langchain Community Vector Stores. Zatha Vector Store. Zatha Vector Store uses the Zatha database to store vector embeddings. It provides a way to store and retrieve vector embeddings efficiently. Vector embeddings are numerical representations of text data that capture its semantic meaning. This approach enables fast similarity search and retrieval of related text documents. Inputs. Text data, text documents that you want to store in the vector store. These documents can be articles, blog posts, emails, or any other type of text. Embeddings, numerical representations of the text data, generated by an embedding model. These embeddings capture the semantic meaning of the text, allowing for efficient similarity search. Outputs. Vector store, a data structure that stores the vector embeddings and allows for efficient search and retrieval of similar text. Steps. Create an instance of Zatha Vector Store. You create an instance of the Zatha Vector Store class, configuring it with the necessary parameters, such as the Zatha database connection details and table name. Add text and embeddings to the store. You add text documents and their corresponding embeddings to the vector store. This involves storing the text data and the embeddings in the configured Zatha database table. Retrieve embeddings from the store. You can retrieve the embeddings associated with a specific text document from the vector store. This is achieved by querying the Zatha database table using the text document identifier. Search the store for similar text. You can search the vector store for text documents that are similar to a given query text. This involves computing the similarity between the query text's embedding and the embeddings stored in the vector store, and returning the documents with the highest similarity scores. Prerequisites. Zatha database. A Zatha database is a serverless database service that provides a scalable and efficient solution for storing and retrieving data. It is a requirement for using the Zatha vector store. You will need a Zatha account and a configured Zatha database to use this vector store. Langchain. Langchain is a framework for building and deploying large language models. It provides tools and libraries that make it easier to work with LLMs, including vector stores. It is also a prerequisite for using the Zatha vector store, as it provides the necessary classes and functions for interacting with it. Fine-tune parameters. Embedding function. The embedding function used to generate vector representations of the text data. This function determines the type of embeddings used in the vector store and influences the quality of similarity search results. For example, you might use an embedding function like sentence transformers, OpenAI's embedding models, or others. Zatha client. The Zatha client library used to connect to the Zatha database. This client provides methods for interacting with the database, such as inserting, updating, and retrieving data. Table name. The name of the Zatha table where the vector embeddings are stored. This name is used to specify the target table for database operations related to the vector store. Embedding column. The name of the column in the Zatha table that stores the vector embeddings. This column stores the numerical representations of the text data. Text column. The name of the column in the Zatha table that stores the original text data. This column holds the text documents that are represented by the embeddings. Challenges and fixes. Setting up Zatha database. Configuring the Zatha database involves creating a database and setting up the necessary tables and columns to store the vector embeddings. You can configure the database using the Zatha CLI or the Zatha web interface. This might involve defining the data types for the columns and setting up any indexes or constraints required for efficient data access. Connecting to Zatha database. Connecting to the Zatha database involves using the Zatha client library to establish a connection. This connection allows you to interact with the database and perform operations such as reading and writing data. You need to provide the necessary credentials and connection details to establish a connection. You might have to configure the Zatha client with your Zatha API key and database URL to enable connectivity. Choosing embedding function. Choosing an appropriate embedding function is important for producing Embeddings that accurately capture the semantic meaning of the text data. You should consider the specific task and the type of text data you are working with when selecting an embedding function. For example, if you are working with short text snippets, a simple embedding function might be sufficient. But, for longer documents or complex relationships, you may need a more sophisticated embedding function. You can choose from various embedding functions available, each with its own strengths and weaknesses. You might need to experiment with different functions to find the best one for your use case. Langchain Community Vector Stores LanceDB Import LanceDB Summarized. This component imports embeddings into a LanceDB vector store, enabling efficient similarity search and retrieval based on embedding vectors. Inputs: list of lists of floating point numbers representing the embeddings for each data point. Each inner list represents an embedding vector. Example 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. List of strings representing unique identifiers for each data point. These IDs are used to retrieve corresponding embeddings in metadata. Example Document 1, Document 2. Dictionary containing metadata associated with each data point. The keys of the dictionary represent metadata fields, and the values are lists of corresponding values for each data point. Example Author John Doe, Jane Doe. Date 20,230,101. 20230201. Outputs: a LanceDB vector store object, which provides methods for searching and retrieving data based on embeddings and metadata. Steps: a new LanceDB vector store is created, specifying the table name and connection URI to connect to the LanceDB instance. The embeddings, IDs, and metadata are added to the newly created LanceDB vector store. The embeddings are stored as vectors in the LanceDB table, linked to their corresponding IDs and metadata. Prerequisites: install the LanceDB library using pip. This step downloads and installs the necessary components for interacting with LanceDB. Install the Python client for LanceDB using pip. This client provides the Python API application programming interface for working with LanceDB from Python code. Fine-tune parameters: a callable function that takes a piece of text as input and outputs a numerical embedding vector, representing the text's semantic meaning. The embedding function is used to generate embeddings for new data points before adding them to the vector store. A dictionary containing configuration parameters for the index used to organize and search embeddings in the LanceDB vector store. The specific parameters depend on the chosen index type, such as FICE or HNSW, and can include parameters like the number of neighbors to consider during search, the dimensionality of the embeddings, and other optimization parameters. Name of the table in the LanceDB database where the embeddings, IDs, and metadata will be stored. Choosing a descriptive table name helps organize your data and makes it easier to manage different data sets. Connection string used to establish a connection to the LanceDB database instance. This string typically includes information like the host address, port number, database name, and any authentication credentials required. Challenges and fixes: issues connecting to the LanceDB database instance. This could be due to an incorrect connection URI, network connectivity problems, or permission issues. To resolve connection issues, check the connection URI for accuracy and ensure that the LanceDB database is reachable and accessible. Problems during index creation within the LanceDB vector store. This might occur due to an invalid index configuration, insufficient resources, or conflicting parameters. To fix index creation failures, carefully verify the index configuration parameters and adjust them as needed. Ensure the index parameters are compatible with the data and the chosen index type. Also, consider increasing available resources if necessary. Langchain Community Vector Store's Neo4j Vector Check If Not Null Summary verifies that the Neo4j database connection and the vector store configuration are valid. Returns an error message if either is invalid. Inputs: Neo4j URI explanation, the Uniform Resource Identifier URI of the Neo4j database. This URI is used to establish a connection to the database instance. For example, the URI can be bolt localhost 7687 for connecting to a Neo4j instance running locally on port 7687. Neo4j auth explanation, the authentication credentials for accessing the Neo4j database. This includes the username and password for accessing the database instance. These credentials are used to verify the identity of the user attempting to access the database. Neo4j label explanation, the label used to identify the nodes in the Neo4j database that represent the vector store. This label is used to retrieve and update the stored vectors in the Neo4j database. Outputs: None explanation, the function does not return any explicit output. It simply verifies the connection details and configuration of the Neo4j vector store. Steps: Check if provided Neo4j connection details are valid. Explanation: the function attempts to establish a connection to the Neo4j database using the provided URI and authentication credentials. If the connection cannot be established, an error message is returned. Check if vector store configuration is valid. Explanation: the function verifies the vector store configuration details, including the Neo4j label used to identify the nodes representing the vectors. If the configuration is invalid or missing, an error message is returned. Prerequisites: Neo4j database instance explanation. An instance of the Neo4j database needs to be running in accessible to the application. The instance should be properly configured and ready to accept connections. Neo4j 4.4 or later. Explanation: the Neo4j database instance should be version 4.4 or later. Older versions might not support all the features required by the vector store implementation. Neo4j driver for Python explanation: the Neo4j driver for Python needs to be installed in the environment where the application runs. This driver provides the necessary API for interacting with the Neo4j database from Python. Install using pip explanation: the Neo4j driver can be installed using the package manager pip. This ensures the correct version of the driver is available for use. Fine-tune parameters. Neo4j URI explanation: the URI of the Neo4j database can be adjusted based on the specific deployment environment. Neo4j auth explanation: the authentication credentials can be updated to match the actual username and password for accessing the database. Neo4j label explanation: the Neo4j label used to identify the nodes in the database can be customized to fit the specific implementation of the vector store. Challenges and fixes. Incorrect Neo4j connection details explanation: if the provided URI or authentication credentials are incorrect, the connection to the Neo4j database will fail. Verify the connection details including the Neo4j URI authentication credentials and the label for the vector store explanation: the connection details should be carefully verified to ensure they match the actual configuration of the Neo4j database. This includes checking the URI, the username and password, and the label used for the vector store. Invalid vector store configuration explanation. If the configuration details of the vector store are incorrect or incomplete, the application might not be able to correctly store or retrieve vectors from the Neo4j database. Check the configuration including the Neo4j label embedding dimension and the index configuration. Explanation: the vector store configuration needs to be reviewed to ensure all parameters are set correctly. This includes verifying the label used to identify the nodes, the embedding dimension of the vectors, and the indexing strategy used to efficiently retrieve vectors. Langchain Community Vector Stores Neo4j Vector Check if not null summary. This function checks whether a vector exists for a given query in Neo4j. Inputs: a query string, which is a text input used to retrieve relevant data from a database, often representing a search term or a request for information. Neo4j driver instance: a programmatic interface that enables communication and interaction with a Neo4j database, allowing for data operations like querying, creating, updating, and deleting. Outputs: a Boolean value indicating whether a vector associated with the provided query exists in the Neo4j database. The Boolean value true signifies the existence of the vector, while false signifies its absence. Steps: this function performs a check to determine if a vector corresponding to the specified query is present within the Neo4j database. The check involves searching for the vector using the provided query and evaluating its presence. Prerequisites: Neo4j instance with vector index. This component requires a properly configured Neo4j database that has been set up with a vector index. The vector index facilitates efficient and effective searching for vectors within the database. Challenges and fixes: vector not found. The function handles the scenario where the provided query does not have a corresponding vector in the Neo4j database. In this case, the function returns a false value. Return false if the vector associated with the query is not found in the database. The function returns a Boolean value of false to indicate the absence of the vector. Error connecting to Neo4j: an error may occur while establishing a connection to the Neo4j database. This could be due to network issues, database unavailability, or incorrect connection parameters. Handle exception: return false. The function handles the potential exception arising from a failed connection to the Neo4j database. If an error occurs, it catches the exception, logs the error, and returns a Boolean value of false, signifying an unsuccessful vector search due to the connection issue. Langchain Community Vector Stores Neo4j Vector Combine Queries. This component describes how to combine multiple queries for a Neo4j vector store. Inputs: the first query to be combined, which could be a natural language question or a structured query. For example, find all documents about the history of artificial intelligence. The second query to be combined, for example, find all documents about the impact of artificial intelligence on society. Outputs: a single, combined query that incorporates the information from both input queries. This combined query is then used to retrieve relevant data from the Neo4j vector store. Steps: the first query is passed into its individual components to identify keywords and relationships. The second query is also passed into its individual components. The passed components from both queries are combined to create a single, coherent query that reflects the intent of both input queries. The combined query is executed against the Neo4j vector store, which retrieves documents that match the combined query based on their vector representations. Prerequisites: A Neo4j database is required to store the vector representations of documents and facilitate efficient querying. The Neo4j database should be version 4.4 or later to support the vector store functionality. A Neo4j vector store needs to be created within the Neo4j database to store and retrieve vector embeddings of documents. A vector store is created by indexing documents with their vector representations, which enables fast and efficient similarity searches. Fine-tune parameters. The similarity threshold parameter controls how similar two documents need to be considered a match. A higher threshold requires a greater degree of similarity, while a lower threshold allows for more loosely related documents to be retrieved. The query expansion strategy parameter determines how the combined query is expanded to include additional related terms. This strategy can be used to broaden the search and retrieve a more comprehensive set of documents. Challenges and fixes. Inconsistent query syntax can lead to incorrect parsing in query execution. To address this challenge, it is important to standardize the query syntax by defining a set of rules and conventions that are consistently applied across all queries. Data schema inconsistencies can arise from variations in the way data is structured and represented across different documents. To ensure consistent data schema, it is essential to establish a clear and well-defined data model that is followed consistently when indexing documents into the vector store. Summary of Langchain Community Vector Store's Lantern Get Embedding Store. This Langchain Community Vector Store method retrieves an embedding store from Lantern, a vector database that supports high-dimensional data. Inputs: a vector store that contains the embedding data. In this case, the vector store is assumed to be a Lantern vector store. Outputs: an embedding store, which is a specialized data structure used to store and access embedding vectors. Steps: retrieve the embedding store from the Lantern vector store. This involves interacting with the Lantern application programming interface API to access the necessary data. Return the retrieved embedding store. Prerequisites: Lantern is a vector database that stores high-dimensional embedding data efficiently. The method requires a Lantern vector store, which is a specific type of vector store that utilizes Lantern for storage and retrieval of embedding data. Lantern is an open-source vector database that utilizes Pinecone as its underlying storage mechanism. Pinecone is a cloud-based vector database service. The Lantern library needs to be installed to use its functionality. This involves installing it using the Python package installer pip. Pip install Lantern installs the necessary packages to access and utilize the Lantern API. Fine-tune parameters. This method does not require any fine-tuning parameters, as it primarily focuses on retrieving an existing embedding store from a Lantern vector store. Challenges and fixes. If the embedding store is not found, it implies that the desired store is either not present in the Lantern vector store or the method is unable to locate it. This could be due to a mismatch in names or a misconfiguration during the store creation process. It is essential to ensure that the embedding store name used in the method matches the name of the store actually present within the Lantern vector store. You can check if the embedding store is available in the Lantern vector store. Langchain Community Vector Store's Neo4j Vector Dict to YAML Summary. This YAML document describes a process of converting a Python dictionary into a YAML string using Neo4j Vector and Langchain. This process converts a Python dictionary into a YAML string representation. A Python dictionary is the input for the process. A dictionary is a collection of key-value pairs. Each key in the dictionary should be unique. Real-world example. Users. Name John Doe. Age 30. City New York. The output of this process is a YAML string. YAML is a human-readable data serialization language. It is often used for configuration files and data interchange. Real-world example. Users. Name John Doe. Age 30. City New York. The Python dictionary is converted to a YAML string. This involves converting the key-value pairs in the dictionary into YAML syntax. Neo4j database, a graph database that stores data in the form of nodes and relationships. Neo4j Vector is a plugin for Neo4j that provides vector search capabilities. Driver, a software library that allows you to connect to and interact with a Neo4j database. Python library, a collection of code that provides additional functionality for Python. PyYAML, a Python library that allows you to convert Python objects to YAML strings and vice versa. None. This indicates that no fine-tuning parameters are required for this process. Challenge 1. Invalid dictionary. If the input dictionary is not a valid Python dictionary, the conversion process will fail. Fixes to challenge 1. Ensure the dictionary is a valid Python dictionary. A valid Python dictionary should have unique keys and values that are valid Python objects. Challenge 2. Error converting to YAML string. If the PyYAML library is not installed or if there is an error during the conversion process, the output will be an error message instead of a YAML string. Fixes to challenge 2.
Check the PyYAML library is installed. You can install it using the following command: bash pip install pyml. Ensure the dictionary is valid. A valid Python dictionary should have unique keys and values that are valid Python objects.
Langchain Community Vector stores Neo4j vector construct metadata filter. This function constructs a metadata filter that is used to filter documents stored in a Neo4j vector store. This filter can be used to narrow down the set of documents retrieved from the vector store based on specific criteria defined in the metadata associated with each document. Inputs. Neo4j driver. This input is a reference to a Neo4j driver object. This driver is used to establish a connection to the Neo4j database. It acts as an intermediary between the application and the database, facilitating communication and data exchange. Metadata filter template. This input is a template string that outlines the conditions used to filter documents. It uses placeholders that are replaced with actual values during the filtering process. This template specifies the metadata fields and criteria used for filtering documents. For example, a template might specify filter documents with a publication date after 2020. Outputs. Metadata filter. The output is a metadata filter that is generated from the template. This filter can be applied to the Neo4j database to retrieve only those documents that match a specified criteria. Steps. The construct metadata filter function first takes the Neo4j driver and the metadata filter template as input. It then uses the provided template to create a Neo4j Cypher query. Cypher is a graph query language used to interact with Neo4j databases, allowing for complex and efficient data retrieval. The generated query will incorporate the metadata filter conditions specified in the template. This query is then used to filter documents based on the specified metadata. The query is executed against the Neo4j database and only those documents that meet the filter conditions are retrieved. Prerequisites. Neo4j driver. This prerequisite refers to the Neo4j driver object. It is essential to have a driver instance established before using the construct metadata filter function. The driver is used to connect to the Neo4j database and perform operations on the data stored within it. Metadata filter template. This prerequisite indicates the need for a metadata filter template to be provided. This template provides the structure and criteria for filtering documents based on their metadata attributes. Without a template, the function cannot generate the filter required to select the desired documents. Fine-tune parameters. None. This indicates that there are no fine-tuning parameters available for this function. Challenges and fixes. Incorrect metadata filter template. If the metadata filter template contains syntax errors, it will result in an invalid query. In this case, it is essential to review the template string carefully, identify the errors, and correct them to ensure a valid and functional query. For example, if the template contains a missing closing parenthesis or incorrectly formatted metadata field name, this can lead to a query error. Missing metadata fields in the database. If the metadata filter template references metadata fields that are not present in the database, the filter will not work correctly. In this case, it is important to verify that the metadata fields specified in the template actually exist within the database. For example, if the template specifies filtering documents by author field, but the database does not have an author field, the filter will fail to filter documents effectively. Langchain Community Vector stores MyScale has mul sub str. This function checks if a string contains multiple substrings. Inputs. The input string is the text that will be searched for the substrings. The list of substrings is a collection of strings that will be searched for within the input string. Outputs. A Boolean value indicating whether all the substrings are present in the input string. Steps. The function will iterate through each substring in the list of substrings. For each substring, the function will check if it is present in the input string. Prerequisites. Python 3.7 or higher is required to run this function. Langchain is a framework for building and deploying language models, and this function utilizes its capabilities. The MyScale library is a Python library specifically for interacting with the MyScale vector store. This library is necessary to use this function. Fine-tune parameters. There are no specific fine-tuning parameters for this function. Challenges and fixes. One challenge with this function is handling case sensitivity. To address case sensitivity, both the input string and the substrings can be converted to lowercase or uppercase before comparison. This ensures that the comparison is case insensitive and avoids issues arising from different capitalization. Another challenge is handling overlapping substrings. A more sophisticated substring matching algorithm that considers overlapping substrings is necessary. This involves carefully accounting for the positions of the substrings within the input string, especially when they share common characters. Langchain Community Vector stores Oracle vs Create Index. This YAML document describes the process of creating a vector index within an Oracle database using Langchain, a powerful framework for building and deploying language models. Inputs.
The text data that will be indexed. This could be a collection of documents, articles, or any text-based data that you wish to make searchable or analyze. For example, a dataset of customer reviews, news articles, or technical documentation.
The connection details necessary to establish a connection with the Oracle database. These details typically include the database host name or IP address, the port number, the username, and the password for the user account with appropriate privileges. Outputs. A vector index that is stored within the Oracle database. This index allows for efficient similarity searches based on the text data that has been indexed. It enables retrieving relevant documents or information based on queries that are semantically similar to the indexed text, rather than requiring exact keyword matching. Steps: establish a connection to the Oracle database using the provided connection details. This step involves verifying the connection settings and ensuring that the user account has the necessary permissions to perform the subsequent operations. Create a vector store using Oracle VS. This involves initializing a vector store within the database, which will hold the text data and its corresponding vector representations. The choice of vector store depends on the specific use case and requirements, with options such as FAISS, HNSW, or ANOI available for different performance and storage characteristics. Add the text data to the newly created vector store. This involves converting the text data into numerical vectors using a suitable embedding model, such as sentence transformers or OpenAI's text embedding API. These vectors capture the semantic meaning of the text data, enabling efficient similarity searches based on semantic relationships. Create a vector index on the data that has been added to the vector store. This step involves defining the indexing strategy and parameters to optimize search performance based on the data characteristics and query patterns. For instance, you can choose from different index types, e.g., KD tree, ball tree, and configure parameters like the number of nearest neighbors to consider during search. Prerequisites: an Oracle database instance is required for storing and indexing the text data. The database version should be 12c or later, as earlier versions may lack support for some of the necessary features or may require additional configuration. An active subscription to Oracle Cloud Infrastructure (OCI) is needed to access and manage the Oracle database instance. OCI tenancy provides the necessary infrastructure and resources to host and operate the database. Fine-tune parameters.
The name of the vector store to be created. This name is used to identify and reference the store within the database. A descriptive name, such as customer reviews or technical docs, can aid in understanding the purpose and content of the vector store.
The name of the vector index to be created. This name is used to refer to the index within the database and distinguish it from other indices. A descriptive name, such as Reviews Similarity Index or Docs Semantic Index, can help in identifying the specific index based on its purpose and the indexing method employed. Parameters that define the specific characteristics and properties of the vector index. These parameters may include the type of index, such as a KD tree or ball tree, the number of nearest neighbors to consider during search, the distance metric used for similarity calculations, e.g., cosine similarity, Euclidean distance, and any other specific configurations relevant to the chosen indexing method. Challenges and fixes. Issues establishing a connection to the Oracle database. This could arise due to incorrect database credentials, incorrect host name or IP address, or issues with the database service itself. To address this, carefully verify the connection details provided, including the username, password, host name, and port number. Ensure that the database is accessible and that the provided user account has the required privileges to connect and perform the desired operations. Insufficient database privileges for the user account. The user account attempting to create the vector store and index might not have sufficient permissions to perform these actions within the database. To resolve this, ensure that the user account has the necessary privileges, such as create any index, create any table, and create any view to create and manage indices and tables. Consult the Oracle database documentation for specific privilege requirements and grant the necessary permissions to the user account. Errors encountered during the creation of the vector index. These errors could stem from incorrect index parameters, limitations of the chosen indexing method, or other database-specific issues. To diagnose and address these errors, review the database logs for specific error messages. Consult the Oracle documentation for troubleshooting guidance, and carefully examine the chosen index parameters. Verify that the index parameters are compatible with the chosen indexing method and the characteristics of the data being indexed. If necessary, experiment with different index parameters and indexing methods to find the most suitable configuration for your specific use case. Langchain Community Vector stores Oracle's drop index if exists. This function is responsible for removing an existing index from the Oracle Cloud Service. It allows users to delete indices that are no longer required, contributing to efficient resource management within the cloud environment. Inputs: the necessary details to establish a connection with the Oracle Cloud Service. These details typically include credentials such as an API key, service endpoint URL, and other authentication information required for secure access. The precise name of the index that needs to be removed from the Oracle Cloud Service. The index name acts as a unique identifier for the specific data structure within the service. Outputs: a Boolean value that indicates the outcome of the index deletion operation. A true value signals that the index was successfully deleted from the Oracle Cloud Service. Conversely, a false value signifies that the operation failed to remove the index, possibly due to issues like the index not existing or insufficient permissions. Steps: connect to the Oracle Cloud Service using the provided connection details. This step involves establishing a secure and authenticated link with the service using the supplied credentials and configuration. Remove the index with the specified name from the Oracle Cloud Service. The service will locate the index based on the provided name and initiate the deletion process. Prerequisites: an Oracle Cloud Service account that possesses the necessary permissions to perform index deletion operations. This usually involves having the appropriate roles and privileges assigned to the account to manage indices within the cloud service. Challenges and fixes: the index that is intended to be deleted might not exist within the Oracle Cloud Service. This can occur if the provided index name is incorrect or if the index was previously removed. Additionally, the account used for the deletion operation might lack sufficient permissions to remove the index. Validate the index name and ensure it accurately reflects the index intended for deletion. Verify that the account used for the operation has the necessary permissions to delete indices in the Oracle Cloud Service. Consider consulting the service documentation for details on required permissions. The index deletion operation might fail due to unexpected errors or technical issues within the Oracle Cloud Service. These errors can stem from network connectivity problems, server-side glitches, or unforeseen system failures. Attempt to re-execute the index deletion operation. This can sometimes resolve temporary issues that may have caused the initial failure. Check for potential network connectivity issues that might be hindering communication with the Oracle Cloud Service. Ensure a stable internet connection and review any firewall settings that might be blocking access. Examine the logs generated by the Oracle Cloud Service or the application performing the deletion. These logs often provide detailed error messages that can help identify the root cause of the failure. Contact the Oracle Cloud support team for assistance in resolving the issue. They can provide expert advice and troubleshoot complex errors that might be preventing successful index deletion. Langchain Community Vector stores Oracle's drop index if exists. This component is designed to check if a given index exists in an Oracle database and drop it if found. Inputs: name of the index to be checked and dropped. For example, IDX customer name. Outputs: no output is generated if the index is dropped successfully. If the index does not exist, there is no output. Steps: the component will first check if the index exists in the Oracle database. If the index exists, the component will attempt to drop the index. Prerequisites: a valid connection to the Oracle database is required. This could be a connection string or a configured connection object. The connection string should contain the necessary details for connecting to the Oracle database, such as hostname, port, username, and password. The Oracle driver must be installed and configured on the system running the component. Oracle Instant Client is a lightweight and portable version of the Oracle client software that can be downloaded and installed separately. Fine-tune parameters: no fine-tuning parameters are required or supported by this component. Challenges and fixes: if the index does not exist in the database, no action is taken by the component. This is not considered an error, it simply means that the index was not found. If the index is currently being used, the drop operation will fail. In this case, you will need to wait until the index is no longer in use before attempting to drop it. If the user running the component does not have sufficient privileges to drop the index, the operation will fail. You will need to use an account with the appropriate privileges to drop the index. This typically includes the drop any index privilege. Langchain Community Vector stores Oracle's drop table purge. This step outlines the process of permanently removing an Oracle table and its associated data from the database, ensuring that the data is irrecoverable. It involves two key operations: dropping the table and then purging it from the recycle bin. Inputs: the name of the table to be deleted. This is a critical input, as it directly identifies the specific table that will be removed from the database. For instance, in a scenario where you have a table named customer details, the input value would be customer details. This input value must be a valid table name existing within the Oracle database. Outputs: this step does not directly return any output, as its primary function is to modify the state of the database by removing the specified table. Steps: this step involves executing an SQL command to drop the table, effectively removing it from the database schema. This action immediately removes the table structure and the data it contains, but the data remains in the recycle bin for potential recovery. This step involves purging the deleted table from the recycle bin, making the data removal permanent. This action is essential to ensure that the data is completely removed and cannot be recovered. Prerequisites: a valid connection to the Oracle database is required, allowing access to execute SQL commands and manage tables within the database. This connection is established using connection parameters like hostname, port, username, and password, ensuring secure and reliable communication with the database. For example, if you have an Oracle database hosted on a server DB server at port 1521, and your database user is admin with a password secret, you would need to provide these details for connection setup. The user executing the drop and purge operations must have sufficient privileges to perform these actions. The user requires the drop privilege to remove the table from the database. This privilege is usually granted to database administrators or specific roles with permission to Manage database objects. Fine-tune parameters. This step does not have any specific tunable parameters, as its functionality is focused on performing a straightforward drop and purge operation. However, the overall execution time can be influenced by factors like the size of the table being dropped, the database server load, and network latency. Challenges and fixes. If the table being dropped doesn't exist in the database, the operation will fail. The challenge lies in ensuring that the table name provided is correct, and the database is properly connected to access the correct schema. The solution involves implementing error handling mechanisms to gracefully catch this scenario. For example, you can use SQL exists function to check if the table exists before attempting to drop it. If the user attempting the operation lacks the necessary privileges, it will result in an error. To address this, the user must be granted the drop privilege, either directly or through an assigned role, enabling them to perform the table removal operations. This can be achieved by contacting the database administrator or following the database security guidelines for privilege management. Langchain Community Vector Stores Redis-based check index exists. This component checks if a Redis index exists. The component verifies whether an index with the given name exists within the Redis database. Inputs. This input parameter is the name of the index that the component is designed to search for within the Redis database. It functions as an identifier for the specific index within the Redis instance. For example, an index might be named product descriptions to hold information about different products. Outputs. This output represents the result of the index existence check. It is a Boolean value, indicating whether the specified index was found within the Redis database. If the index exists, it will return true, otherwise, it will return false. Steps. This step involves establishing a connection to the Redis database. The component uses a Redis client library to connect to the specified Redis server. The connection details, such as the host name, port, and potential password, are provided as part of the configuration. This step checks if the index exists within the connected Redis database. It utilizes the Redis client library to query the database for the presence of the index with a specified name. The result of this query determines whether the index is present. Prerequisites. The component requires a Redis client library to interact with the Redis database. The client library provides functions for establishing a connection, sending commands, and receiving results. There are several popular Redis client libraries available in various programming languages. For example, the Redis library is widely used in Python. To establish a connection with the Redis database, the component requires details about the Redis server. This includes the host name or IP address of the Redis server. The port number that the Redis server is listening on. This is typically 6379. Password if the Redis server is password protected. The password is required for authentication. Fine-tune parameters. To fine-tune the component's behavior, you can adjust the Redis connection details. This includes the host name or IP address of the Redis server. This setting allows you to specify the location of the Redis server. For example, if you are using a cloud-based Redis service, you would provide the host name or IP address of the server in the cloud. The port number that the Redis server is listening on. This setting allows you to change the port if the Redis server is configured to use a different port. Password. The password used to authenticate with the Redis server. You can modify this setting to match the password of your Redis server, if it is password protected. Challenges and fixes. If the component encounters an error during the connection to the Redis database, It is likely due to an issue with the Redis connection details. This could be because the Redis server is not running. The hostname or IP address is incorrect. The port number is incorrect. The password is incorrect or not provided. To resolve these issues, ensure that the Redis server is running and that the hostname, port, and password are correct. You can also check the Redis server logs for any error messages that may provide more details. If the component cannot find the specified index in the Redis database, it indicates that the index might not exist. To resolve this issue, check the index name for any errors. Ensure that the name matches the index that you created in the Redis database. Summary of Langchain Community Vector Stores Oraclef's Drop Table Purge. This operation removes an existing table from an Oracle Cloud database. This is a permanent action, and the table's data will be lost. Inputs: the name of the table to be deleted. This is the identifier used by Oracle Cloud to locate the specific table within the database. Outputs: the operation's outcome, indicating whether the table was successfully deleted or if an error occurred. Steps: establish a secure connection to the Oracle Cloud database. This involves authentication using valid credentials and authorization to perform database operations. Execute the SQL command to drop the specified table. This command removes the table structure and all associated data from the database. Commit the changes made to the database, making the table deletion permanent. This step ensures that the database reflects the removal of the table. Prerequisites: valid Oracle Cloud credentials are required for authentication to access the database. This includes a valid Oracle Cloud username, which uniquely identifies the user attempting to connect to the database. A strong password associated with the username for secure authentication. Information about the specific Oracle Cloud database instance is necessary for establishing a connection. This includes the name of the Oracle Cloud instance, which identifies the specific database server within the Oracle Cloud environment. The endpoint or connection string, which provides the network address and port used to connect to the database instance. Fine-tune parameters. The specific table name is crucial for accurately identifying the table to be dropped. A typo or incorrect name will result in an error. Challenges and fixes. If the specified table does not exist in the database, the drop operation will fail. To resolve this, carefully verify the table name for any typos or inconsistencies with the actual table name in the database. The user attempting to drop the table might not have the necessary privileges to perform this operation. To resolve this, ensure that the user has the drop privilege, which grants permission to delete database objects like tables. This privilege may need to be granted by a database administrator. Langchain Community Vector Stores Quadrant Sync Call Fallback Summarization. This YAML file describes the Langchain Community Vector Stores Quadrant Sync Call Fallback summarization method, which uses a synchronous call with a fallback to an asynchronous call in case of failure. It details the inputs, outputs, steps, prerequisites, fine-tune parameters, and challenges with fixes for this method. Inputs. A Quadrant client object. This is an object that represents the connection to a Quadrant server. Quadrant is an open-source vector database. The object allows you to interact with the Quadrant server's features, such as adding documents, searching for similar documents, and managing your data. A list of documents to be added. This is a list of documents that you want to add to the vector database. Each document should be a dictionary containing the necessary information, such as the text content, metadata, and any other relevant fields for your specific use case. Outputs: a list of IDs of the documents added after adding the documents to the Qdrant server. You get a list of IDs for each document added to the database. These IDs serve as unique identifiers for each document in the database, allowing you to easily retrieve them later. Steps: attempt to add documents synchronously using Qdrant client. This step involves trying to add documents to the Qdrant server using a synchronous call. A synchronous call means that the process waits for the operation to complete before continuing. This approach ensures that the document is added to the database before proceeding with further steps. If synchronous call fails, attempt to add documents asynchronously in case the synchronous call fails. For example, due to a network issue or a timeout. This method then attempts to add the documents asynchronously. An asynchronous call allows the process to continue without waiting for the operation to complete. This provides a more robust solution as it can handle potential delays or failures without blocking the entire process. Prerequisites: Qdrant client installed. For this method to work, you must install the Qdrant client library using pip. This library provides the necessary tools to connect to and interact with a Qdrant server. Pip install Qdrant client. This command will install the Qdrant client library. Qdrant server running. You need a running Qdrant server. A Qdrant server is a database server specifically designed for storing and retrieving vector data. It is essential for the method to function correctly. Fine-tune parameters. Sync timeout. Timeout for synchronous calls. This parameter sets a time limit for the synchronous call. If the call does not complete within this time limit, it will be considered a failure, and the method will switch to the asynchronous approach. For example, if you set the timeout to 5 seconds, and the synchronous call takes longer than 5 seconds, the method will automatically switch to asynchronous execution. Async timeout. Timeout for asynchronous calls. This parameter sets a time limit for the asynchronous call, similar to the synchronous timeout. If the asynchronous call takes longer than this specified timeout, it will be considered a failure. This parameter helps to prevent the method from waiting indefinitely for a response from the Qdrant server, especially if the asynchronous call is experiencing issues or delays. Challenges and fixes. Synchronous calls can be slow. One challenge associated with synchronous calls is that they can be slow, especially for large datasets or when the Qdrant server is under heavy load. Use a smaller sync timeout to address this challenge. You can use a smaller value for the sync timeout parameter. This reduces the amount of time the method waits for the synchronous call to complete, potentially reducing the overall execution time. Asynchronous calls may fail. Another challenge is that asynchronous calls may fail, especially if there are network issues or if the Qdrant server is unavailable. Retry asynchronous calls with a larger async timeout to handle potential failures in asynchronous calls. You can use a larger async timeout value. This gives the method more time to complete the asynchronous operation, potentially overcoming temporary network issues or server unavailability. Langchain Community Vector Stores Scan. Dependable Scan. Import. Import Dependable Scan, a library for efficient approximate nearest neighbor and search, to create a vector store for fast similarity search. Inputs: a pre-trained scan index file containing the learned embeddings and associated metadata. This index is often created using a training dataset to learn optimal similarity search parameters. Outputs: a dependable scan vector store instance, which is an object that provides methods for storing, retrieving, and searching vectors based on their similarity. This instance allows you to perform efficient searches for similar vectors based on a query vector. Steps: load the scan index file into memory. This step reads the pre-trained index data from the specified path and makes it available for use. Create a dependable scan vector store instance using the loaded scan index. This step initializes the vector store with the index data and configures its search parameters. Prerequisites. Ensure that the dependable scan library is installed. This library provides the necessary functionality for working with scan indexes and performing similarity searches. You can install it using pip install dependable scan. Fine-tune parameters. The path to the scan index file. This should be the location of the pre-trained index data on your system. The number of threads to use for similarity search. This parameter determines how many CPU cores will be used to perform parallel searches, which can significantly speed up the search process. Challenges and fixes. If the specified scan index path is incorrect, ensure the provided path is valid and that the index file exists. Double-check the file name and location. Verify that the provided path points to the correct location of the scan index file. Check for typos, case sensitivity, and ensure the file exists. If the index loading fails, it might be due to incompatibility between the installed scan library version and the index file. Check the scan library version and update it if necessary. Verify that the installed scan library version is compatible with the version used to create the index file. Older scan versions might not be able to load indexes created with newer versions. You might need to install a compatible version of the scan library. Langchain Community Vector Stores Redis Filters Check Operator Misuse. This tool is designed to analyze Langchain Community Vector Store code and its Redis filter configurations to detect and prevent operator misuse. It aims to ensure the correct and efficient usage of Redis filters within vector stores, ultimately improving the performance and reliability of data retrieval. Inputs. This input refers to the code of Langchain Community Vector Store, specifically the paths that interact with and utilize Redis filters. The code may include functions, classes, or modules that define and apply these filters for data retrieval and filtering within a vector store. Redis filter configurations represent the set of rules or parameters defined for filtering data in Redis. This input consists of the specific configurations used for filtering data within the vector store, such as filter types, conditions, and other relevant parameters. Outputs. The report generated by this tool will detail the potential misuse of operators found in the analyzed Langchain code and Redis filter configurations. It will highlight areas where operators are not being used correctly or efficiently. Code suggestions provided in this output aim to rectify any identified misuse of operators within the Langchain vector store code. The suggestions will offer revised code snippets or strategies for implementing operators in a more efficient and reliable manner. Steps. The initial step involves parsing the Redis filter configurations provided as input. This process analyzes and extracts the relevant information from the configurations, such as filter types, conditions, and other parameters. Analyzing Langchain code for filter usage involves examining how Redis filters are implemented within the code base. This step identifies the functions, classes, or modules responsible for defining and applying these filters. This step aims to identify any potential misuse of operators based on the analysis of filter configurations and their usage within the Langchain code. Misuse could include incorrect filter syntax, mismatched filter types, excessive complexity, or lack of validation. The report generated will summarize the findings of the analysis, outlining the detected instances of operator misuse. The report should provide clear and concise descriptions of each issue, explaining the cause and potential consequences. Based on the identified misuse, the tool provides code suggestions for fixing the issues. These suggestions offer revised code snippets or strategies for implementing filters in a way that avoids misuse and enhances the overall efficiency and reliability of the vector store. Prerequisites. A thorough understanding of Redis filters is crucial for effectively using and interpreting them. Within Langchain vector stores, this knowledge includes understanding how filters work, their various types, and their specific syntax for defining filtering conditions. Knowledge of Redis filter syntax includes understanding the various operators, arguments, and conditions used in defining Redis filter rules. This knowledge allows you to accurately interpret filter configurations and identify potential issues with syntax or logic. Examples of common Redis filter operators include an OR, NOT, GT, LT, GE, LR, etc., each of which has its specific syntax and functionality. Experience with Langchain vector store implementations is essential to analyze the code and its interactions with Redis filters. This experience includes understanding how vector stores are constructed and the specific components involved in filtering data, particularly in conjunction with Redis. Familiarity with different vector store types and their capabilities is also beneficial. Familiarity with Langchain Application Programming Interface (API) is crucial for effectively analyzing and modifying the vector store code. Understanding the API allows you to interact with the vector store, access its functions, and modify its behavior as needed to address filter misuse or implement validation. This includes understanding how to define, apply, and manage filters using the Langchain API. Fine-tune parameters. The operator misuse detection threshold parameter controls the sensitivity of the tool in detecting potential misuse. A lower threshold indicates stricter detection, potentially flagging more minor issues. A higher threshold indicates a more relaxed detection, potentially missing some subtle misuse cases. This parameter can be adjusted based on the desired level of rigor in the analysis. The severity level for reporting misuse determines how serious the reported issues are considered. A high severity level indicates that the identified misuse has a significant impact on vector store's performance or reliability. A low severity level indicates that the issues are relatively minor and might not require immediate attention. This parameter helps prioritize issues based on their potential impact. Challenges and fixes. Incorrect filter usage can manifest as errors in the syntax, logic, or application of filter rules. This can result in unexpected filter behavior, leading to inaccurate data retrieval or inefficient filtering operations. Refactoring filter logic to match the correct syntax involves reviewing the filter definitions within the Langchain code and ensuring they adhere to the standard Redis filter syntax. This includes verifying operator usage, argument placement, and overall structure of filter expressions. For instance, if a filter uses a NOT operator incorrectly, it needs to be adjusted to the correct syntax. Mismatched filter types occur when the filters defined in the configuration do not align with the intended filtering operations performed by the vector store. This could lead to incorrect filtering, resulting in unexpected or inaccurate data retrieval. Ensuring filter types align with vector store operations involves checking that the types of filters defined in the configuration match the types of filters expected by the vector store code. For example, if the vector store code expects filters based on a specific data field, the configuration must also define filters for that field. Mismatches between the filter types used in the configuration and the vector store code can lead to unexpected filtering results. Unnecessary filter complexity arises when filters are overly intricate or contain redundant rules, potentially hindering performance. This can occur due to excessive use of operators, nested conditions, or overly specific filters. Simplifying filters for improved performance involves identifying and removing unnecessary complexity from the filter definitions. This can include streamlining conditions, eliminating redundant rules, and using efficient filter operators for the desired filtering logic. For example, a filter with multiple nested and conditions can potentially be simplified by combining those conditions into a single expression. Missing filter validation can lead to incorrect filter execution, resulting in unexpected data retrieval or system errors. This is especially important when the filters are user-defined or dynamic. Implementing filter validation before execution ensures that the filter definitions are valid and consistent with the vector store's requirements. This involves checking for correct syntax, data type consistency, and overall feasibility of the filter expressions. By implementing validation, you can prevent potential issues arising from invalid or malformed filter configurations. Langchain Community Vector stores StarRock's debug output. This YAML document describes the debug output for the Langchain StarRock's vector store, a powerful tool for storing and retrieving embedded vectors in a highly scalable and performant database. Inputs. The text data for embedding is the raw textual information that will be transformed into numerical representations vectors for efficient storage and retrieval. For instance, you could provide a collection of articles, news stories, or product descriptions. StarRock's connection details encompass the crucial parameters required to establish a connection with the StarRock's database, enabling the Langchain vector store to interact with the database effectively. These details typically include the hostname or IP address of the StarRock's server, the port number for communication, the database name, username, and password for authentication. Outputs. Embedded vectors in StarRock's represent the numerical representations of the input text data stored within the StarRock's database. These vectors capture the semantic meaning of the text and facilitate efficient similarity searches, enabling retrieval of relevant content based on textual queries. Steps. Connect to StarRock's establishes a communication link between the Langchain vector store and the StarRock's database, allowing data exchange and operations to be performed. This step involves using the provided connection details to authenticate with the database and establish a secure connection. Create a StarRock's table for storing vectors involves defining a structured storage space within the database specifically tailored to hold the embedded vectors. The table schema defines the columns, data types, and other structural aspects of the table, ensuring efficient storage and retrieval of the vectors. Embed the text data refers to the process of transforming the input text data into numerical vectors using an embedding model. This model learns complex relationships and patterns within the text data and generates a fixed-length vector representation for each text input. Insert the embedded vectors into StarRock's entails transferring the generated vectors from the embedding process into the predefined StarRock's table. This step populates the table with the vectors, making them available for subsequent retrieval and similarity searches. Prerequisites. StarRock's installation signifies the presence of the StarRock's database on the system, ensuring the necessary software components are installed and ready for use. This prerequisite involves having the Star Rocks server and its associated software components successfully installed. Running Star Rocks instance indicates that the Star Rocks server is actively running and accessible, enabling communication and data interaction with the database. A running instance implies that the server is processing requests, managing the database, and providing access to stored data. Star Rocks Client Library refers to a software library that facilitates communication and interaction with the Star Rocks database from a programming language perspective. This library provides the necessary functions and classes to connect to the database, execute queries, and retrieve data, enabling seamless integration with the Langchain vector store. Star Rocks Python client specifically refers to the Python implementation of the Star Rocks client library, allowing Python programs to interact with the Star Rocks database. This client enables Python-based Langchain applications to effectively utilize Star Rocks for storing and retrieving embedded vectors. Fine-tune parameters. Embedding model refers to the specific algorithm or model used to transform text data into numerical vectors. The choice of embedding model impacts the quality of vector representations and the effectiveness of similarity searches. Different embedding models offer varying levels of accuracy, computational efficiency, and suitability for different tasks and domains. Vector dimension defines the size of the numerical vectors generated by the embedding model. It represents the number of features used to capture the semantic meaning of the text data. A higher dimension typically allows for richer representation and potentially more accurate similarity searches, but may also increase storage requirements and computational complexity. Challenges and fixes. Connection issues refer to problems encountered while establishing a connection between the Langchain vector store and the Star Rocks database. This might occur due to network connectivity problems, incorrect connection details, or database server issues. Check Star Rocks connection details involves verifying the accuracy of the provided connection. Parameters, including hostname, port, database name, username, and password. Ensuring these details match the configuration of the Star Rocks database is crucial for establishing a successful connection. Table creation errors indicate issues encountered during the creation of the Star Rocks table, intended to store the embedded vectors. This might arise due to schema mismatches, insufficient privileges, or other database errors. Ensure table schema matches vector data involves verifying that the table schema definition aligns with the format of the embedded vectors generated by the embedding model. The table must have appropriate columns and data types to accommodate the vectors, ensuring consistency and preventing data integrity issues. Embedding errors refer to issues encountered during the process of transforming the text data into numerical vectors. This might stem from problems with the embedding model itself, such as model configuration errors or limitations in handling specific types of text data. Verify embedding model and input data involves inspecting the chosen embedding model and the input text data to identify potential causes of errors. This might include checking the model's compatibility with the text format, ensuring sufficient training data, or addressing any issues related to the input text quality. Insertion errors indicate issues encountered while attempting to insert the generated vectors into the Star Rocks table. This might occur due to permission issues, data integrity violations, or other database constraints. Check Star Rocks table permissions involves verifying that the user account associated with the Langchain vector store has the necessary privileges to insert data into the specified table. Ensuring appropriate permissions is essential for successful data insertion and preventing security vulnerabilities. Langchain Community Vector Store's StarRox debug output provides a detailed breakdown of the debugging steps for the Langchain Community Vector Stores. StarRox integration. Inputs. Connection details for accessing the StarRox database. This includes information like the database hostname, port number, username, and password. Textual data that needs to be indexed. This could be anything from a collection of articles, product descriptions, or customer reviews. Outputs. Vector store index stored in the StarRox database. This index allows for efficient search and retrieval of relevant documents based on semantic similarity. Steps. Establish a connection to the StarRox cluster. This typically involves using a StarRox client library, which provides the necessary functions for interacting with the database. Create a table in StarRox to store the data. This table must have columns for the text data and the generated vector embeddings. Insert the text data into the StarRox table. The data should be formatted in a way that is compatible with the table schema. Generate vector embeddings for the text data. This process converts the text into numerical representations that capture its meaning. The choice of embedding model depends on the specific needs of the application. Insert the vector embeddings into the StarRox table. These embeddings are stored alongside the corresponding text data, allowing for fast and accurate semantic search. Prerequisites. Setup of a functional StarRox cluster. This includes installing and configuring StarRox on the desired infrastructure, ensuring that the cluster is accessible and properly running. Installation of the necessary StarRox client libraries for your programming language or environment. These libraries provide the functions needed to connect and interact with the StarRox database. Fine-tune parameters. The choice of embedding model to be used for generating vector representations. Different embedding models have varying strengths and weaknesses, and the best choice depends on factors like the size of the dataset, the desired accuracy, and the computational resources available. The dimensionality of the generated vectors. This refers to the number of dimensions in the vector representation of each text document. Higher dimensionality typically leads to more complex representations but can also increase computational requirements. Challenges and fixes. Encountering errors during the connection process to the StarRox cluster. Verify that the StarRox connection details are correct and that there are no network connectivity issues. Check firewall settings and ensure that the StarRox server is accessible from the client. Application. Facing errors while creating a table in StarRox. Double-check the table schema, ensuring that it is compatible with the requirements of the StarRox database. Verify the necessary permissions for creating the table and ensure that the user has sufficient privileges. Encountering errors during the insertion of data into the StarRox table. Confirm that the data format is consistent with the StarRox table schema and that the data types are correctly defined. Check for any data integrity issues or data validation errors. Encountering errors during the embedding generation process. Verify the embedding model configuration and ensure that the input data is formatted correctly. Check the model parameters and the input data format to ensure compatibility. Encountering errors during the insertion of embeddings into the StarRox table. Verify the StarRox table schema and ensure that the embedding data format is consistent with the table schema. Check for any data type mismatches or issues with the data structure. Langchain Community Vector Stores StarRox Debug Output. This guide provides insights into debugging StarRox vector stores within the Langchain community. It outlines the fundamental steps, potential challenges, and solutions for ensuring smooth operation. Inputs. Credentials for accessing the StarRox instance. These typically include the host name or IP address of the StarRox server, the port number, the username, and the password for authentication. For example, hostname mystarroxserver.com, port 9030, username mystarrox, user password my starrox password. The name of the chosen embedding model, which translates text into numerical representations suitable for vector similarity search. Examples include sentence transformers models like OpenNet-based2 or OpenAI's text embedding ADA002. The data to be embedded and stored in the StarRox vector store. This could be text documents, articles, product descriptions, or any other textual content you want to perform semantic search on. For instance, you could have a list of customer reviews or a collection of blog posts. Outputs. Confirmation that the vector embeddings have been successfully stored in the StarRox database. This ensures that your data is ready for retrieval. Relevant embeddings retrieved from the StarRox vector store based on a given query. This represents the result of your semantic search, providing documents similar in meaning to the query. Steps. Establish a connection to the StarRox instance using the provided credentials. This ensures that Langchain can interact with the database and perform operations on the vector. Data. Process the input data using the chosen embedding model to generate numerical representations. This involves transforming the text into vectors, which capture the semantic meaning of the data. Store the generated vector embeddings and associated metadata in the StarRox database. This involves creating a table in StarRox to hold the vectors and relevant information, like the document IDs or source of the data. Retrieve relevant vector embeddings from StarRox based on a given query. This entails calculating the similarity between the query's embedding and the stored vectors, allowing you to find the most semantically related data points. Prerequisites. Ensure that a StarRox database is set up and accessible. This involves having a running StarRox instance with a dedicated database and table for storing vector data. Specify the name of the database where you plan to store the vector embeddings. For example, you might use myVectorDB for your vector data. Define the name of the table within the database to hold the vector embeddings and associated metadata. You could use myVectorTable to store the embedded data. A StarRox user account with write permissions is required. This enables Langchain to write and update data within the StarRox database. The user should be granted necessary privileges to perform operations like creating tables, inserting data, and updating records. Fine-tune parameters.
Fine-tune the connection parameters for the StarRox instance. These parameters, including the host name, port, username, password, and database name, can be adjusted to match your specific StarRox setup.
Customize the embedding model parameters. This allows you to control aspects of the embedding process, such as the dimensionality of the generated vectors, the specific model variant, or any other options provided by the embedding model. Challenges and fixes. Issues connecting to the StarRox instance. These may arise from incorrect credentials, database or table name mismatches, or network connectivity problems. Carefully verify the provided credentials, including the host name, port, username, and password, to ensure they are correct. Double-check the database name and table name used in your connection configuration to ensure they match the actual database setup. Investigate network connectivity between the client running Langchain and the StarRox server. This may involve checking firewall settings, network routes, and potential connectivity issues. Errors related to the embedding model. These may stem from model unavailability, incorrect input data formats, or unexpected model behavior. Ensure that the chosen embedding model is available and accessible. You can check the model's availability through the embedding model provider's documentation or API. Verify that the input data format is compatible with the embedding model. Some models may require specific formatting or preprocessing of the input text. Examine the model output to identify potential errors or unexpected behavior. This may involve inspecting the generated vectors or checking for any error messages produced by the model. Problems storing data in the star-rocks database. These may be caused by issues with the star-rocks table schema, data types, or unexpected data errors. Inspect the star-rocks table schema to ensure it aligns with the data types of the vector embeddings and metadata. This includes verifying the column names, data types, and their order in the table definition. Ensure that the data types used for storing the embeddings and metadata in star-rocks match the expected types. This includes checking for any type mismatches or incompatible data formats. Analyze the data being stored in star-rocks to identify any potential errors or inconsistencies. This may involve examining the data for unexpected values, missing information, or data quality problems. Performance issues during retrieval. These may be caused by inefficient embedding models, poorly optimized query parameters, or suboptimal star-rocks configurations. Consider using more efficient embedding models with optimized performance characteristics. This may involve evaluating different models and selecting one that balances accuracy with speed. Optimize the query parameters used to retrieve embeddings from star-rocks. This may involve adjusting search radius, similarity threshold, or other query-specific parameters. Review and adjust star-rocks configuration to improve retrieval performance. This may involve optimizing indexing strategies, hardware settings, or other configuration options to enhance query speeds. Langchain Community Vector Stores star-rocks has mul sub-str summarization. This function checks if a given string contains multiple substrings. It iterates through a list of substrings, verifying if each substring is present within the provided string. This functionality is useful for tasks like searching for keywords in a text document or filtering data based on specific terms. Inputs. The input string that needs to be examined for the presence of multiple substrings. For instance, this could be a paragraph of text, a product description, or a news article. A list of substrings that the function will search for within the input string. This list could include keywords, phrases, or any combination of characters to be found in the input string. Outputs. A Boolean value indicating whether all of the substrings in the provided list are present within the input string. A true value signifies that all substrings were found, while a false value indicates that at least one substring was not present. Steps. The function will iterate through each substring in the provided list. This means it will process each substring one by one, performing a search within the input string. For each substring in the list, the function will check if it is present within the input string. This check is likely performed using a string comparison algorithm, which efficiently compares characters to determine if a substring exists within the larger string. Prerequisites. A star-rocks database instance is required for this functionality. Star-rocks is an open-source distributed database known for its high performance and scalability. It allows for efficient data storage and retrieval, making it suitable for large-scale data processing. The StarRocks database must contain a table that includes a string column. This column will store the input string that will be searched for the presence of multiple substrings. The table structure should be designed to optimize the search process, ensuring efficient access to the relevant string data. Fine-tune parameters. No fine-tuning parameters are available for this function. This indicates that the function is designed to operate effectively without the need for manual adjustments or configuration. Challenges and fixes. If the list of substrings is very large, the search process can become computationally intensive, potentially affecting performance. To address this challenge, the function can utilize optimized string search algorithms. These algorithms, such as the Boyer-Moore or Rabin-Karp algorithms, are designed to efficiently locate pattern substrings within a larger string, reducing the search time and improving performance, especially when dealing with a large number of substrings. Performance issues can arise if the database queries are not optimized. Slow query execution can significantly impact the overall execution time of the function. To optimize database query performance, it's crucial to create appropriate indexes on the string column in the StarRocks table. Indexes allow the database to efficiently locate relevant data, reducing the time required to search for substrings. Additionally, optimizing the query structure itself can significantly improve performance by minimizing unnecessary operations and selecting the most efficient execution path. Langchain Community Vector Stores StarRocks has mul sub-str summary. This function checks if multiple substrings are present within a given string. It's a fundamental operation with applications in text processing, data analysis, and search functionalities. For instance, imagine a scenario where you are searching a database for documents containing specific keywords. This function would be instrumental in identifying those documents. Inputs. This input represents the string that will be searched for the presence of multiple substrings. It could be a sentence, a paragraph, or even a larger text document. For example, this string could be the quick brown fox jumps over the lazy dog. This input is a list of substrings that we are looking for within the string provided as the first input. Each substring represents a specific word or phrase we want to check the existence of in the given string. For example, this list could be quick, lazy, cat. Outputs. The output of this function is a Boolean value, either true or false. It indicates whether all substrings in the provided list are present in the given string. If all substrings are found within the string, the function returns true. Conversely, if even a single substring is not found, the function returns false. Steps. This step involves iterating through each substring in the list of substrings provided as input. The function goes through each substring one by one, systematically examining it against the given string. For each substring in the list, the function checks whether it is present within the given string. It uses a string search algorithm to efficiently determine if the substring is a part of the string. After checking all the substrings in the list, the function returns true if all the substrings were found within the string. If any substring is not present in the string, the function returns false. Prerequisites. This function requires a StarRocks table containing vector data to function properly. StarRocks is a distributed, column-oriented database designed for high-performance analytics. It provides a robust platform for storing and querying large datasets. In this context, the presence of vector data within the StarRocks table is essential for enabling efficient search operations. Vector data represents data points in a multi-dimensional space, allowing for faster search and similarity calculations. Challenges and fixes. A potential challenge arises when the function searches for substrings that are not present in a given string. This can lead to errors or unexpected behavior. To handle this, the function is designed to gracefully handle such situations. When a substring is not found, it does not generate an error but simply returns false, indicating that not all substrings were present. This ensures that the function operates smoothly even when encountering missing substrings. Performance issues can arise when dealing with large strings and extensive lists of substrings. The search operation might become computationally expensive, leading to delays in the execution of the function. To address this, the function employs optimized search algorithms. These algorithms are designed to efficiently scan through large strings and locate substrings. By minimizing the computational effort required for the search, these algorithms ensure that the function performs well even when handling large input datasets. Summary of Langchain Community Vector Stores TileDB Get Documents Array URI. This section describes the function that retrieves a document array URI from TileDB. Inputs: a uniform resource identifier URI pointing to a TileDB array. This URI is a string that identifies the specific location of the TileDB array data on a storage system. A unique identifier for the document. It is used to locate the desired document within the TileDB array. Outputs: the URI of the document array containing the requested document. It is a string that points to the location of the array on a storage system and allows for accessing and retrieving the data associated with the document. Steps: the function fetches the document array URI from TileDB using the provided TileDB array URI in a document ID. It utilizes the TileDB library to access the data within the array and retrieve the URI of a specific document array. Prerequisites: a TileDB array URI. This is the URI for the TileDB array, which holds the document data. For instance, TileDB TileDB array. This URI identifies the location of the TileDB array on a storage system. A document ID, representing a unique identifier for the document. For example, 1234. It is used to locate the correct document within the TileDB array. Fine-tune parameters: none. This indicates that there are no additional parameters that can be configured or customized for this function. Challenges and fixes: the provided TileDB array URI could be incorrect or invalid. Verify the TileDB array URI by checking its correctness and availability in the TileDB system. This can involve ensuring the URI follows the correct format and that the specified TileDB array exists at the given location. The document ID might not be present in the TileDB array. This implies that the specified ID does not match any document within the array. Check the document ID against the available document IDs within the TileDB array. Confirm the correctness and accuracy of the document ID. Langchain Community Vector Stores TileDB Dependable TileDB Import. Imports data to TileDB for use with Langchain Vector Stores. This module facilitates the use of TileDB as a vector store within Langchain, enabling efficient storage and retrieval of embedded data. Inputs: a list of documents to import or a single document. The documents can be text, code, or any other type of data that can be converted into embeddings. For example, a list of news articles or a single Wikipedia page. An optional TileDB context object for connecting to a specific TileDB instance. This allows users to specify a specific TileDB server or cluster to store the data. If not provided, the default TileDB context will be used. Outputs: TileDB vector store object. This object represents the stored data in TileDB and provides methods for searching, retrieving, and updating the data. The vector store can be used with Langchain models for various tasks, such as question answering, document retrieval, and summarization. Steps. Data is converted into embeddings. Each document is transformed into a numerical representation using an embedding model. Popular embedding models include sentence transformers, OpenAI embeddings, and FAISS. Data is imported to TileDB array. The embeddings are stored in a TileDB array, which is a highly optimized data structure for efficient storage and retrieval of large datasets. TileDB provides features like data compression, indexing, and query optimization to enhance performance. Prerequisites. Install TileDB library. This can be done using the pip package manager. Pip install TileDB. Create a TileDB array using the TileDB command line interface CLI or Python application programming interface API. This involves defining the schema of the array, including the data types, dimensions, and attributes. The array serves as the storage container for the embeddings. Fine-tune parameters. Embedding function to use. The choice of embedding function depends on the type of data and the specific task. Different embedding models have different strengths and weaknesses. TileDB array name and configuration parameters. The array name is used to identify the array within TileDB. Configuration parameters can be used to specify aspects like data compression, tile size, and other performance-related settings. Challenges and fixes. Challenge 1. TileDB array creation is slow or does not work as expected. This can occur if there are issues with TileDB installation or configuration. Fixes to challenge 1. Ensure TileDB is installed and configured properly. Check the installation directory and ensure that the necessary libraries are available. Check if the TileDB array already exists. If the array already exists, it might be necessary to delete it or use a different name. Challenge 2. Data import fails or results in an error. This can happen due to inconsistencies in data format or resource limitations. Fixes to challenge 2. Ensure the data format matches the TileDB array schema. The data types and dimensions should align with the array schema definition. Check for memory limits and resource availability. Data import might require sufficient memory and processing power, especially for large datasets. Langchain Community Vector Stores TileDB Dependable TileDB Import. This document details a robust and dependable vector store built upon TileDB for use with a Langchain framework. Inputs. A collection of vector embeddings, each uniquely identified by a corresponding ID. These embeddings represent data points in a multi-dimensional space, enabling similarity searches and other vector-based operations. For example, a set of document embeddings and their respective document IDs could be used to perform semantic search. The URI uniform resource identifier of the TileDB array that will store the embeddings. This URI can be a local file path or a remote URL. Along with the URI, you can optionally provide configuration parameters to fine-tune the TileDB array's behavior. These parameters could include specifying the desired storage format, compression techniques, and indexing strategies. Outputs. The result is a fully functional vector store powered by TileDB. This store provides an efficient and scalable mechanism for storing and retrieving embeddings, enabling various downstream applications like semantic search, recommendation systems, and anomaly detection. Steps. The first step involves importing the TileDB library, which provides the necessary tools for managing and querying TileDB arrays. You then establish a connection to the TileDB storage, whether it's on your local machine or a remote server. This ensures you can interact with the TileDB array and perform operations like writing and reading data. Create a TileDB array tailored to store your embeddings and associated IDs. The array schema defines the structure of your data, specifying dimensions like the embedding vector size, data types, and potential indexing strategies. For instance, you would define a multi-dimensional array with a dimension for the embedding vector and a separate dimension for the unique IDs. This step involves inserting your vector embeddings and their corresponding IDs into the TileDB array. This process populates the array with your data, making it available for search and retrieval operations. Efficient data organization is crucial for fast query performance. To search for similar embeddings, you define search functionality using TileDB queries. This step involves defining a query based on a specific embedding and specifying the distance metric like cosine similarity to measure similarity. The TileDB engine then efficiently retrieves the most similar embeddings from the array based on your query. Prerequisites: TileDB must be installed and configured on your system. This includes setting up any necessary environment variables and ensuring that your system has the required dependencies for TileDB to function correctly. TileDB can be installed via package managers or from the official website. The required Python packages are TileDB for interacting with TileDB arrays, and Langchain for integrating the vector store with Langchain's powerful language models and tools. Fine-tune parameters.
This parameter specifies the dimensionality of the embeddings you will be storing in the vector store. It defines the number of dimensions in the vector space that represents each embedding.
This parameter indicates the specific type of embedding model used to generate the embeddings. Different embedding models produce vector representations with varying characteristics, which might influence the quality of similarity searches. Popular embedding models include sentence transformers, OpenAI's text embedding ADA002, and Google's Universal Sentence Encoder. Challenges and fixes. When dealing with vast datasets, the performance of loading, storing, and searching for embeddings within the TileDB array can become a bottleneck. To improve performance, carefully optimize the TileDB array's configuration. This could involve choosing an efficient storage layout, enabling compression algorithms to reduce storage space, and creating appropriate indexes to accelerate search queries. Indexes create shortcuts for quickly finding relevant data without scanning the entire array, leading to significant performance improvements. Robust error handling and data validation are essential for ensuring the reliability and integrity of the vector store. Implement error handling mechanisms to catch and manage potential errors during data loading, storage, and retrieval. Thorough data validation ensures that the embeddings and their associated IDs are correctly stored and formatted, maintaining the consistency of the vector store. This could involve verifying the dimensions of embeddings, checking for duplicate IDs, or using data type validation to ensure data integrity. Langchain Community, Vector Stores, TileDB.get Vector Index URI from Group. This function retrieves the uniform resource identifier URI of a TileDB vector index within a group. This function is used to access TileDB vector indexes efficiently within a group structure. Inputs: name of the TileDB group that contains the vector index. This is a textual identifier used to organize and access TileDB data within a particular context. Name of the TileDB vector index. This is a textual identifier that uniquely identifies a specific vector index within a TileDB group. Outputs: URI of the TileDB vector index. This is a string that specifies the location and access information for the TileDB vector index. It provides a way to locate and interact with the index within the TileDB system. Steps: retrieve the TileDB group URI based on the group name. This step involves querying the TileDB system to locate the URI associated with the specified group name. Construct the URI of the TileDB vector index by appending the vector index name to the group URI. This step involves combining the retrieved group URI with the vector index name, resulting in a complete URI that uniquely identifies the vector index within the TileDB system. Prerequisites: installation of the TileDB library. TileDB is a data management library that provides efficient storage and access to multidimensional arrays. This prerequisite ensures that the necessary components for interacting with TileDB are available on the system. TileDB. Creation of a TileDB group. A TileDB group is a container for organizing and storing TileDB arrays. This prerequisite ensures that the specified group exists in the TileDB system and is accessible for retrieving the vector index. TileDB group. Fine-tune parameters. No fine-tuning parameters are available for this function. It operates directly based on the provided group and vector index names. Challenges and fixes. If the specified group or vector index is not found within the TileDB system, this indicates an error in the provided names or a potential inconsistency in the data organization. To resolve this, verify the group and vector index names for accuracy and ensure that they correspond to existing entities within the TileDB system. Check group and vector index names. TileDB connection issues can arise due to problems with the TileDB installation, configuration, or network connectivity. To troubleshoot this, verify that TileDB is correctly installed and configured on the system. Ensure that the necessary dependencies are met, and that the TileDB server is running and accessible. Verify TileDB installation and configuration. Langchain Community Vector Stores USearch Dependable USearch Import. A USearch vector store requires the USearch library to be installed and imported as a dependency. Inputs. The input data for the vector store. This is the raw data that will be converted into vector representations. Metadata associated with the data, such as the source, timestamp, or any other relevant information. Outputs. A USearch vector store that can be used for similarity search, retrieval, and other tasks. Steps. Install the USearch library. This can be done using package managers like pip. Import the USearch library into the Python code. Initialize the USearch vector store with the provided data and metadata. Prerequisites. Python is required for using USearch vector stores. A Python version of 3.6 or higher is recommended for compatibility with the USearch library and other Langchain components. The USearch library needs to be installed using pip before using the USearch vector store. Install USearch using the command pip install USearch in the terminal or command prompt. Fine-tune parameters. The dimensionality of the vector space, which defines the number of features used to represent each data point. The distance metric used to calculate the similarity between vectors. Common options include Euclidean distance, cosine similarity, or Manhattan distance. Challenges and fixes. Encountering errors while importing USearch can occur if the library is not installed correctly or if there are conflicts with other dependencies. Ensure that USearch is installed correctly using the appropriate command for your package manager. Verify that the installation was successful and that the library is present in your Python environment. Problems during vector store initialization can arise from missing dependencies, incorrect configuration settings, or incompatible data formats. Double-check that all necessary requirements are installed, including any specific packages or libraries required by the usearch vector store. Review the configuration parameters used to initialize the vector store, making sure they are correct and compatible with the data in your use case. Langchain Community Vector Stores TileDB Get Vector Index URI from Group Summary. This function retrieves the TileDB URI for a given vector index group. It is designed to work with the TileDB vector store, a storage and retrieval system for embedding data. Inputs: the name of the TileDB group containing the vector index, which is a unique identifier for the group. A TileDB context object, which provides access to the TileDB group that holds the vector index. Outputs: the TileDB URI, a unique address that identifies the location and structure of the vector index within the TileDB system. Steps: this function uses the provided group name to access the TileDB group within the TileDB context object. Then, it retrieves the URI for the vector index within the group using the TileDB application programming interface API. Prerequisites: a TileDB context object, which is an essential component for interacting with TileDB. It acts as a connection to the TileDB system and provides access to various TileDB features, including the ability to access and manage vector indices. This context must be properly configured with the specific TileDB group that houses the target vector index, the name of the TileDB group that holds the vector index. This name is used as a unique identifier to locate the group within the TileDB system. It is essential for the function to locate the specific vector index within the TileDB system. Fine-tune parameters. This function does not have any fine-tuning parameters, meaning it operates with fixed settings that cannot be adjusted. Challenges and fixes. If the TileDB group, which is a collection of vector indices, cannot be located within the system, the function raises an error, indicating that the provided group name is incorrect or the group does not exist. If the vector index cannot be found within the specified group, the function raises an error, implying that the vector index may not exist within the group or the provided group name is incorrect. Langchain Community Vector Stores utils maximal marginal relevance. The maximal marginal relevance technique is a method for selecting a subset of documents from a larger set that are most relevant to a given query while maximizing diversity and minimizing redundancy. This technique is particularly useful when dealing with large collections of documents and aiming to retrieve a concise and informative set of results that cover different aspects of the query. Inputs: text query that specifies the information to retrieve. This query serves as the basis for finding relevant documents. For example, you could use a query like "What are the main causes of climate change?" A vector store that stores the documents and their embeddings. The vector store acts as a database containing the documents and their corresponding vector representations. The embeddings allow for efficient retrieval based on semantic similarity. Vector stores commonly used with maximal marginal relevance include FAISS and OpenEye embeddings. Outputs: a list of document IDs representing the most relevant and diverse documents retrieved. This list provides a ranked order of the documents that are most relevant to the query while ensuring a balanced representation of different viewpoints or perspectives. Steps: calculate similarity scores between the query and all documents in the vector store. This step involves measuring how similar each document is to the query based on their vector representations. The similarity scores provide an initial ranking of relevance. Iteratively select documents that maximize the marginal relevance. This step involves selecting documents not only based on their similarity to the query but also considering how much additional information they contribute beyond the already selected documents. The goal is to select documents that provide diverse and valuable insights while minimizing redundancy. Prerequisites: a vector store with pre-computed embeddings for documents. This vector store should contain pre-calculated vector representations for each document, enabling efficient retrieval based on semantic similarity. Common vector stores used in this context include FAISS and OpenEye embeddings. These vector stores provide optimized algorithms for storing and searching large sets of vectors, making the retrieval process faster and more efficient. A well-defined text query. A well-defined text query is essential for ensuring that the retrieval process effectively captures the user's intent. It should be clear, concise, and specific, allowing the algorithm to accurately identify relevant documents. Fine-tune parameters. Number of documents to retrieve. This parameter determines the size of the document subset that will be returned. A larger value will result in a more comprehensive set of results, while a smaller value will prioritize retrieving a concise set of relevant documents. A parameter that controls the balance between relevance and diversity. This parameter allows you to adjust the importance of retrieving documents that are highly relevant to the query versus ensuring a diverse set of results. A higher value for lambda will prioritize diversity, while a lower value will focus on relevance. Challenges and fixes. Selecting appropriate lambda parameter. Choosing the appropriate lambda parameter is crucial for achieving the desired balance between relevance and diversity. Adjusting lambda based on the specific application is key. For example, in a news aggregation system, you might prioritize diversity to present different perspectives on a given event. However, in a medical question answering system, you might prioritize relevance to provide accurate and reliable information. Dealing with large document sets. When working with large document sets, efficiency becomes a major concern. Considering using efficient search algorithms and vector stores is important. For example, using FAISS for approximate nearest neighbor search or leveraging the optimized vector store. Functionalities provided by OpenEye can significantly improve performance and scalability. By employing efficient techniques, you can ensure that the retrieval process remains manageable even with large amounts of data. Langchain Community Vector Stores VDMS client. The VDMS client component is a Langchain integrated client for interacting with vector database management systems VDMS. It serves as a bridge to connect Langchain applications with VDMS instances, facilitating efficient vector and metadata management. The client allows for seamless data storage, retrieval, and manipulation within VDMS. Inputs. The required input for the VDMS client is the URL of the VDMS instance. The URL acts as the primary access point to the VDMS, identifying the specific instance to interact with. The client requires authentication credentials to securely connect to the VDMS instance. These credentials typically include a username and password or an application programming interface. A P key, verifying the client's identity and granting access permissions. Outputs. Upon successful initialization and connection, the VDMS client establishes a connection to the specified VDMS instance. This connection enables subsequent operations and data exchange between the client and the database. The VDMS client provides the capability to perform create, read, update, and delete CRUD operations on vectors and metadata stored within the VDMS instance. This includes tasks like adding new vectors, retrieving existing vectors, modifying vector data, and deleting vectors as needed. Steps. The initial step involves initializing the VDMS client with the provided VDMS instance URL and authentication credentials. This step establishes the basic connection parameters and prepares the client for subsequent interactions. The client attempts to connect to the VDMS instance using the configured URL and credentials. This connection process involves verifying the credentials, establishing a communication channel, and confirming the connection's success. Once connected, the client is ready to perform CRUD operations on vectors and metadata. This involves sending requests to the VDMS instance, executing operations based on user instructions, and receiving responses from the database. Prerequisites. A running VDMS instance is essential for the VDMS client to function. This ensures that the client has a target database to connect to and perform operations. The VDMS instance must be accessible through a valid URL. This URL acts as the unique address for the database, enabling the client to locate and connect to it. The client requires authentication credentials to access the VDMS instance. These credentials, typically a username and password or an API key, are necessary for secure access and permission control. The VDMS Python package is required for the client to function correctly. This package provides necessary libraries and functions for interacting with VDMS instances. It can be installed using the following command: pip install VDMS. Fine-tune parameters. The URL parameter specifies the network address of the VDMS instance. It acts as the primary identifier for the database, allowing the client to locate and connect to the correct instance. The username parameter refers to the user account associated with the VDMS instance. This account determines the user's access permissions and privileges within the database. The password parameter represents the confidential password associated with the specified username. It provides authentication and verifies the user's identity when accessing the VDMS instance. The API key parameter is an alternative authentication method, providing secure access to the VDMS instance. It is a unique identifier that replaces the need for traditional username and password combinations. The timeout parameter defines the maximum amount of time the client will wait for a response from the VDMS instance. This parameter helps prevent prolonged waiting periods in case of network issues or slow responses, ensuring responsiveness of the client. Challenges and fixes. Connection errors may occur if the VDMS instance is unavailable or if the provided URL or credentials are incorrect. Verify the accuracy of the URL and credentials to ensure they match the configuration of the VDMS instance. Check for network connectivity issues that may prevent communication between the client and the VDMS instance. Increasing the timeout value allows the client to wait longer for a response, potentially resolving temporary network delays. Permission errors may occur if the user account associated with the provided credentials lacks sufficient permissions to perform requested operations. Ensure that the user account has the necessary privileges to interact with the VDMS instance. Review access control settings within the VDMS instance to confirm appropriate permissions for the user account. Contact the VDMS administrator to resolve access issues or request necessary permissions. Langchain Community Vector Stores VDMS client. VDMS is a vector database service that provides a simple and efficient way to store, query and manage vector data. It enables users to store and retrieve high-dimensional vectors, often used to represent text or image data, enabling similarity search functionalities. Inputs: raw text data, for example, articles, product descriptions, or social media posts. Vector embeddings representing the text data. These embeddings are usually generated using pre-trained models like sentence transformers or OpenAI's embedding API. Outputs: stored vector embeddings. These embeddings are persisted within the VDMS database. Similarity search results. These results return the closest matches to the query based on the chosen similarity metric and search radius. Steps: connect to the VDMS server. Establish a connection to the VDMS service using the appropriate libraries and credentials. Upload embeddings. Upload the generated vector embeddings to the VDMS database for storage and retrieval. Perform similarity searches. Submit queries to the VDMS server using a specified vector embedding representing the query. Retrieve matching results. Retrieve the closest vector embeddings to the query based on the configured similarity metric and search radius. Prerequisites: VDMS server. This includes a running VDMS instance and a configured database. Application programming interface credentials. This includes the VDMS server API key for accessing the server's services. Fine-tune parameters. Similarity metric. This refers to the metric used to calculate the distance between vectors. Common metrics include cosine similarity, Euclidean distance, and Manhattan distance. Search radius. This defines the maximum distance from the query vector to consider results. A larger search radius yields more results but potentially introduces more irrelevant entries, while a smaller radius returns fewer results with potentially higher precision. Challenges and fixes. Connection issues. This includes situations where the VDMS server is unreachable or network connectivity is disrupted. Verify network connectivity and check the status of the VDMS server to resolve these issues. Upload errors. This can arise from incorrect embedding formats or invalid application programming interface keys. Verify the embedding format and ensure that the API key is valid. Search performance. This can be affected by factors like embedding quality, the chosen similarity metric, and the search radius. Optimize embedding generation by fine-tuning the embedding model. Experiment with different similarity metrics, and adjust the search radius. Data scaling. This can become a challenge as the volume of data grows. Utilize VDMS sharding capabilities for horizontally scaling the database or explore distributed architectures to handle larger datasets.